Am I audible?
Yes, ma'am, you're audible.
Yes, ma'am. Okay.
Hello.
Visible, madam.
Good morning, Tekwani sir. Good morning, sir.
Good morning, madam.
How are you, sir?
Fine. I was just trying to turn on my video. Is it visible? No, no.
No, sir. Video
Just,
is not visible.
just. Am I audible?
Yes, sir.
Vinita,
Yes, sir.
hello, Vinita madam.
Hello. Yes, sir.
Hello.
You can start, madam.
Okay, fine, sir. Hello, I'm audible.
Yes, madam. You are audible.
Before we begin with the program, I would like to reiterate the words by Dr. APJ Abdul Kalam. If four things are followed, having a great aim, acquiring knowledge, hard work, and perseverance, then anything can be achieved. A very good morning to all. Myself, Vinita Chauhan, faculty from Electrical Engineering Department, IIT Indus University, welcome you all to the inaugural function of Gujco's sponsored 3 days workshop on power electronics for renewable energy-based distributed generation. On behalf of Indus University, I welcome our chief guest, Dr. P.N. Tekwani, Dean Faculty of Doctoral Studies and Research, Nirma University, Honorable Executive President, Vice Chancellor, Indus University, Professor Dr. V.K. Srivastava Sir, Dean Academics, Indus University, Dr. Sandeep Chakravarti, Dr. Sujoy Chaudhary, Director IIT, Dr. Jaideep Chakravarti, Head of Electrical Engineering Department, various heads of department, faculty members, students, and my dear participants. Remembering the God before starting any function is our tradition. So I will request all to kindly join your hands for Stuti.
Sound is not there, ma'am.
It's not audible, madam.
Is it audible now?
No.
No, ma'am.
No, no.
आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापं सन्ध्यादीपनमोऽस्तु ते ओ दीपब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः ओ दीपब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश मतिं स्वच्छां हि मे सदा रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् रवेरस्तं समारभ्य यावत् सूर्योदयो सर्वं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः
Thank you, everyone. The purpose of this workshop is to create awareness about the latest trends in power electronic uses in distributed generation. Electricity and the underlying infrastructure for its production, transmission, and distribution are essential to the well-being of society. The rising concerns of climate change and depletion of fossil fuels in the foreseeable future are driving renewable generation developments rapidly. Renewable energy-based distribution and with power electronic has played a vital role in large-scale penetration of renewable generation. The emerging advancement in renewable energy technology seem to make them most economical in near future. Thus, it became necessary for power engineers to understand state-of-art technology for renewable and also the challenges faced by the same. On this context, this workshop is aimed at delivering an overview of power electronics converter, its application, and control for grid-connected renewable energy systems. Moving ahead, I would like to invite Dr. Jaideep Chakravarti, Head of Electrical Engineering Department, for welcome address.
Good morning, all. I am audible.
Yes, sir, you are audible.
Honorable Executive President, Vice Chancellor, Sir, Dr. V.K. Srivastava, Sir. Our chief guest for this inaugural function, P.N. Tekwani, Sir, who is Dean Faculty of Doctoral Studies and Research from Nirma University. Dr. Sujay Chaudhary, heads of the department, faculty members, coordinators, my dear students, and all participants. I am honored to extend my warm welcome to all for this workshop, WUSCO sponsored workshop on power electronics for renewable energy based distributed generation. I am very much grateful to our Honorable Executive President and Vice Chancellor, Sir, for sparing some time from his busy schedule and becoming a part of this inaugural session. Thank you, sir, for joining the inaugural session of our workshop. I am also very much grateful to P.N. Tekwani, sir, who has accepted our invitation to become the chief guest for this workshop. Thank you, sir, for accepting our invitation. I welcome Sujay Chaudhary, sir, Director IIT, for sparing some time and becoming a part of this inaugural session of the workshop. I also welcome all the participants of the workshop, and I'm sure that you all will feel enriched and knowledge after completing this workshop. I also welcome all the faculty members, PhD scholars, industry persons, and all others, those who have registered for this workshop. And I hope that you all will find this workshop highly engaging and fruitful and beneficial for your future ventures. Thank you.
Thank you, sir, for your motivational words. Now, I would like to introduce Dr. Sujay Chaudhary, Director IIT Indus University. Dr. Sujay Chaudhary is serving as Director IIT and Dean Faculty of Technology and Engineering, Indus University. Sir is a Professor of Metallurgical Engineering. He has more than 18 years of academics as well as industrial experience. His research area is physical metallurgy. He was associated with Honeywell International, Torrance, CA, USA from 2007 to 2013. Sir did his postdoctoral from Worcester Polytechnic Institute, USA. Sir has published several papers in various international journals and conferences. He is a member of Sigma Xi, the Scientific Research Society. We welcome you, sir, for inaugural function. Director, sir. Okay. Director sir is having some problem with the mic. We'll move ahead. Now I would like to introduce Honorable Executive President, Vice Chancellor, Indus University, Professor Dr. V.K. Srivastava sir. He is a competent and high-performing professional offering more than 25 years of rich cross-functional experience in all aspects of teaching, research, and administration in higher education sector. His research interests include wastewater treatment, solid waste management, environmental issues of industries, and energy recovery by using plasma technology. Sir is a peer reviewer of large number of research papers being published in reputed high-index national and international journals in research areas. He has published and presented significant number of research papers in national and international journals and conferences. Sir has published number of books and chapters with national and international publishers. He is a recipient of various notable awards and honors. Prior to Indus University, Sir has worked as Vice Chancellor of Sankarchand Patel University, Visnagar for 3 years. We welcome you, sir, for the inauguration function.
Hello. Hello. Am I audible?
Yes, sir, you are audible.
Sujay sir has joined or?
Sir, he has joined, but he's having some issue with the mic.
Okay. Okay. Good morning, one and all. Honorable Chief Guest of today's function, Dr. P.K. Tekwani ji, Director of IIT, Dr. Sujay Chaudhary, Head of the Department Electrical Engineering, Dr. Jaideep, Anchor of the event, Professor Vinita Chauhan, Dr. Rashmi Sharma, and all other participants who are participating in this one-day workshop, that is itinerary of workshop inaugural, that is power electronics for renewable energy based distribution generation. This year, Indus University has decided to celebrate 75th anniversary of our freedom, जिसको हम आज़ादी का अमृत महोत्सव के रूप में मना रहे हैं। इसी उपलक्ष्य में इंडस यूनिवर्सिटी ने ऐसा निश्चय किया कि हम क्यों नहीं आज़ादी के 75वें जन्म दिवस को, इस अमृत महोत्सव को एक अलग ढंग से मनाएं, जिससे कि हमेशा हम इस आज़ादी के अमृत महोत्सव को याद रख सकें। As we are celebrating 75th anniversary of the freedom, so therefore Indus University has decided to organize so many events by the number 75. In the same series, Indus University has decided during this whole year, we will organize, say, 75 workshops, 75 seminars, 75 other programs. So this number is very important for us, and with respect to this number, each department and each institution is contributing to achieve the target of 75. Friends, when we organize any workshop, then naturally there are so many people who gets benefit out of it. There may be several stakeholders. They may be our students of Indus University. They may be the students of other institutions. There may be faculty of our institution, there may be faculty of other institutions as well. But the fundamental objectives of such workshops is to provide the latest information, what are the recent trends, what are the advancements in particular field. Say for example, here the theme of the workshop is power electronics for renewable energy based distribution generation. The topic is very well selected because when we look towards the basket of energy sector, then we find that this renewable energy has great potential because we cannot depend on the fossil fuel. It may be coal, it may be petroleum, or it may be any other product which is consumable and it is having certain reservoir. After some time, you will find that the quantity is totally exhausted. So then in that case, the only option is say the renewable energy. Like in case of renewable energy, India and in particular Gujarat is doing well as far as the solar energy generation is concerned. Gujarat has been always the leading state, particularly for all the initiatives. It may be belonging to energy sector, it may be belonging to climate change, it may be belonging to environment. So friends, I would like to congratulate the electrical engineering department of IIT for selecting such a fantastic topic. And naturally, I'm the member of climate change department, government of Gujarat. So I request to all the participants, those who are participating, all are requested to come out with some wonderful projects or some sort of innovative projects which can really help as far as the renewable sources are concerned and the power generation from renewable sources is concerned. In Charanka, we are having, say, the largest plant which is producing, say, the electrical energy from solar. In Gujarat, we have started so many other projects like canal top, rooftop, etc., etc. So from solar, we are generating huge quantity of electrical energy, which is really very, very useful for us. And at the same time, it is reducing, say, the consumption of fossil fuels and other fuels, which are normally used in thermal power plants and in the other power generation sources. So when we talk about such type of topics, as I have already requested to all the participants, because many of them are holding, say, the PhD degree, and they may be having some wonderful idea in their mind. So I request to all the participants to come out with some innovative projects and submit it to the funding agency. Climate Change Department itself is giving a huge grant, particularly for innovative projects in the field of climate change, in the field of energy sector, particularly in the field of renewable energy. It may be, say, the e-vehicles, it may be e-bikes, bicycle, it may be e-rickshaw, it may be hybrid type of things. In Ahmedabad, probably you people might have seen, say, the hybrid buses by AMTS and other places. So such type of hybridization is taking place. It is not only, say, the electrical vehicles, it is, say, the sort of hybrid vehicles having some innovative approach so that we can reduce the consumption of fossil fuels, maybe petrol, maybe diesel, etc., etc. So on this occasion, I see good number of participants are taking part in this event. And I think as this is the workshop, I request to the organizers to keep this workshop more of giving hands-on experience, more for dialogue mode. It should not be monologue that the speakers are presenting the slides and the students are participants are simply listening. At the end of each presentation, there should be good number of questions which are asked by the participant. Then only we can say that the session is successful. Similarly, at the end, you can have, say, the panel discussion sort of thing, so that more and more participants can get the benefit of this workshop, which is organized by Electrical Engineering Department of IIT. So at this occasion, I convey my best wishes for successful completion of this workshop. Once again, I welcome Professor P.N. Tekwani, sir, who is Dean, Faculty of Doctoral Studies and Research. Thank you very much, sir, for joining us. And to other guests also, to other participants also, on behalf of Indus University, I convey my best wishes. Thank you very much. Thank you.
Thank you, sir.
Thank you, sir, for your inspirational address and motivational words. We will try our best to reach our goals. Now I would like to introduce Chief Guest, Dr. P.N. Tekwani, Dean Faculty of Doctoral Studies and Research, Nirma University. Sir has received PhD degree from Indian Institute of Science, ISC, Bangalore, in the field of multi-level inverter fed induction motor drive. He received Tech Corporation Medal Award of ISC for the best PhD thesis. He is the first rank holder in ME and University first gold medalist in BE. He has total professional experience of more than 23 years. Dr. Tekwani has published more than 90 research papers. His research interests are power electronic converters, power quality, power supplies, and motor drive. He has been serving the Institute of Technology, Nirma University since 2001. Sir is a young associate of Indian National Academy of Engineering and a senior member of IEEE and IEEE Industrial Electronics Society, USA. Sir has won Best Paper Award several times at different national and international conferences. He is a recipient of various prestigious awards like Professor Mohammad Aj Rashid Best Paper Award, Young Engineer National Award, IST L&T National Award, and many more. We welcome you, sir, for inaugural function.
Thank you, Vinita madam. Am I audible?
Yes, sir, you are audible.
Yes. Fine. First of all, thank you very much for inviting me in this particular inaugural session. I just heard various speakers before this, including the faculty members and the Honorable Executive President, sir, Dr. Srivastava, sir. First of all, let me extend my best wishes for the workshop. And it is good that Vinita madam and Rashmi madam, these two faculty members are coordinating particular workshop of 3 days, which is sponsored by Guj Coast. In fact, I remember that this workshop was planned sometime back in the year 2019. But because of pandemic situation, suddenly the lockdown was imposed, and then there was no choice left with us but to postpone it. And then today we are all meeting here through a virtual medium. And you know, in this particular approximately 1.5 years, we have developed this as a new normal. But really speaking, what we can discuss and interact one-to-one may not be exactly possible through this via media, but looking to the need of the times in this testing times, definitely we have to keep the things running and keep doing research, keep interacting. So this is good medium here. Now, coming to the main point of this workshop, the topic is very apt, but at the same time, topic is very challenging also. For all the researchers working in this area, whether doing research by pursuing PhD or post-PhD research, renewable energy-based distributed generation. The name sounds, very good, but here at the same time, it is quite complex issue. And lot of knowledge of control systems, power systems, power electronics, communication engineering, magnetics, digital signal processing, and so many other areas of engineering is demanded. And the researchers will definitely agree with me that it's not merely sufficient that we do some computer simulation studies and remain happy with those models. But on the contrary, what we need is what we need is all of us must see that whatever simulation exercise we are doing, that is finally implemented, and that is quite challenging task. Simulation is one thing, implementation is other thing. But researchers, participants, please understand that when you are submitting a paper in any of the reputed journals, we see that they do not simply accept paper based on simulation studies. Experimental verification is must. Many a times, verifying this kind of distributed generation or even microgrids is not that simple because of its practical complexities, and that is demanding that we need to set up good laboratory facilities. Without good laboratory facilities, it may not be possible for us. See, we cannot go and work on the live grid, but we have to create a prototype in the laboratory where we can really implement our ideas of this power electronic based, renewable energy based distribution generation, microgrids, or even I say now nanogrids. Why not? For implementing or for proof of the concept, even nanogrid is also sufficient. So the main point which I would like to emphasize on is that let us not be satisfied with only simulation studies. We have to go into the depth of the mathematical model, simulation studies, not only the steady state but transient analysis, and then its practical implementation and verification of the concept. Lot of things are already done and lot of things are also being done by researchers worldwide in the area of distributed generation. So as a researcher, what is left for us now? We need to identify the research gap. And identifying research gap itself is a challenging task, because if the research gap is properly identified, then problem is half solved. Because then only we have to think about solution and not about the problem. So we need to take sufficient time to identify the research gap also. And then we need to work on the solution of the problem. So in this sequence, every researcher has to work. So this kind of workshops are not just for, as our Honorable Executive President sir said very rightly, that at the end of every session there should be churning, there should be brainstorming. Maybe at the end of workshop we can have panel discussion where participants are also interacting and discussing their queries, their experience also. This is experience sharing. Nobody is expert here, I understand, because everybody is a learner. Even if after so many years of experience, everybody is a learner, and we keep learning every day some new concept of that technology, I am saying. So it's good that everybody shares the experience and we clear doubts mutually, and we generate one ecosystem where researchers are helping each other. Here, institutes are not the boundaries. Please understand that whether you are working in one institute, I am working in other institute, somebody working in third institute, but no, that's fine. We are all working for the profession, but we must see that our research collaborations must be strengthened, and we help each other in order to, apply or even produce a delta step contribution in the technology, because research is not done, the large jump is not possible overnight. You cannot achieve the targets. Gradually delta steps are to be taken, and that delta contribution will take the technological development further and further. So we must all collaborate, develop good linkages, whether you are a PhD student or you are a PhD supervisor, or because every faculty member has to do research now, almost it is mandatory part of our job. So through these workshops and seminars, we generate the research seeds also, research ideas also, and those research ideas are to be worked upon further. So my sincere request to all the participants that take maximum benefit out of this particular workshop. These 3 days will be very much fruitful in long run if the idea is taken with full spirit. Make use of each and every moment, and then be attentive, ask questions, discuss, and see that you get maximum out of each and every session. I can talk much, but looking to the time given to me, 10 minutes, I would not take much time, because afterwards we have this session, there we can have more discussions. I was seeing the schedule also of the 3 days. Good topics are selected, and thoroughly participating in all these topics, discussions, will definitely lead you to a particular state of mind where you will start thinking about it, and then start identifying the research problems and start working on those. But then starting to work on these problems is not that easy. Again, lot of hard work and practice is required. Even if you want to simulate a small microgrid, it takes its own time. We just cannot simulate it in 1, 2, 3, or 4 days. It takes its own time to develop a model of it. So I mean to say that whether it is simulation, mathematical modeling, concept verification, experiment, it takes its own time, and then it demands perseverance and patience from the researcher. So we all teachers or even researchers must have this particular characteristic in us, that we are having good patience to work with the problem, to see there are some roadblocks also while working in the problems, then finding out some other solution, and then finally contributing into the development of the technology. So I congratulate organizers for organizing such workshop and providing a very good platform for all the researchers to share their ideas and to listen to each other and learn something more in this area. So with this, I thank organizers, and then all the best to all the participants.
Thank you, sir.
Thank you, sir, for such an enthusiastic talk. We'll surely consider your suggestions. We would like to end the formal inaugural function with vote of thanks. I would like to invite Program Coordinator, Professor Rashmi Sharma.
Am I audible, ma'am?
Yes, ma'am.
Yes, madam.
Thank you, ma'am. A very good morning to one and all present here. Respected Chief Guest, Professor Dr. P.N. Tekwani, sir, Dean Faculty of Doctoral Studies and Research, Nirma University. Dr. V.K. Srivastava, sir, Honorable Executive President, Vice Chancellor, Indus University. Dr. Sujoy Chaudhary, sir, Director IIT, Indus University. Dr. Jaideep Chakravarti, sir, HOD Electrical Engineering Department. Dignitaries, session experts from various institutes, faculty members, participants, and my dear students. It gives me an immense pleasure to propose a vote of thanks for this occasion. I, Rashmi Sharma, on behalf of the entire electrical department and Indus University here together, and on my own behalf, extend a hearty vote of thanks for gracing the inaugural function of the 3 days Gujco-sponsored workshop on power electronics for renewable energy-based distributed generation. I extend my sincere vote of thanks to our chief guest, Dr. P. N. Tekwani sir, who spared time from his busy schedule to grace the occasion. Today, we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our near future. It is my honor and privilege to propose vote of thanks to Honorable Executive President, Vice Chancellor Indus University, Dr. V.K. Srivastava sir, for gracing today's inaugural function with thought-provoking and inspiring address. I express my deep gratitude to Dr. Sujoy Chaudhary sir, Director IIT, Indus University, for providing the opportunity to conduct the workshop. I would like to thank our HOD, Dr. Jaideep Chakravarti sir, for his continuous guidance and motivation. I am very much thankful to Gujkos to provide financial support to organize this workshop. Last but not the least, I would like to thank all participants from different institutes for the registration and their active interest in this workshop. Once again, thank you everyone.
Thank you, ma'am. Thank you all for gracing this inaugural function. We'll start our first session in a short while. Request all participants to remain present for the very first session. Thank you. We will start our first session as per the schedule at 11 a.m. Please remain present in the same link. Thank you. Good morning, all. We'll start with our first session. Session 1. The topic of today's session is control of power electronics converters for solar photovoltaic power system and microgrids.
Okay, very good morning. So, madam, now I will share the presentation.
Yes, sir.
Is it visible?
Yes, sir. Screen is visible.
Fine. Okay. So we are starting on time, exactly. It is good. Now, the topic of the session is control of power electronic converters for solar photovoltaic power systems and microgrids. Now, here there are 2-3 points which are to be understood. One is this power electronic, another is solar, and when we say microgrids, these are 3 main points: power electronic, solar photovoltaic, microgrids. Now, microgrid itself has got a large number of components in it, and the microgrid concept is becoming more and more popular because of intervention of more renewable energy sources into our distributed generation. Power electronics, again, without that, it's not possible for us to use the energy uh, coming from different sources, which is not directly in the form of electricity many a times, or not in the usable form. And solar photovoltaic, of course, one of the components of the renewable energy sources. There are others. We will see those in our session. So let us start now. So initially, for a few slides, I would like to draw your attention, because when we say electric power generation today, we have conventional sources, like you can see the thermal, you see the hydro here, nuclear, wind, solar, and many more. So the role of non-conventional, or I say the renewable energy sources, is increasing in our power system. And of course, for the conservation of environment, definitely we would like to have more and more green energy sources, so that environment can be maintained in a good condition, which is good to live for our future generations and this generation also. So now, by introduction of this more and more renewable sources, challenges have increased. Of course, ease has also come because of distributed generation, but it has its own challenges also. And major challenge here is that many of these sources are intermittent in nature. We don't get continuous energy from them. Variable energy comes, and then we need to feed it to a grid, or maybe to a load. And especially when to a load, we cannot feed variable energy to the load. And that's why a lot of processing and control comes into picture. Lot of processing and control comes into picture. And that is why power electronics comes into picture. So we must understand that why it is so important for power electronic to contribute into this new electric power generation system. The role of power electronics was very limited in the conventional power system here, here. But now without power electronics, it's not possible for us to use energy from these new sources. And for that, let us see now how our country is moving. See the total installed electric power generation capacity of India, and this is mind well the latest figure is on 31st August 2021, which is published in September 2021 by Central Electricity Authority, Ministry of Power, Government of India. So these are the authentic figures, the real figures which are released by Government of India. See the total electric power generation capability in India is, see here, 3,88,134 megawatt. Now this is the number today for all the power system, electrical, power electronic engineers. See, this is the number today, the 100% capacity that we are showing. That is 3,88,134, and this is increasing day by day because a lot of new plants are under construction, and we are sure that this number is not constant. Tomorrow when you see, next month when you see, definitely this number will increase. But as on today, now with this, see the sector-wise shares, central sector, state sector, private sector. And private sector has got the majority of share. Almost 48%, 1,86,000 megawatt is being generated by private sector. So here for us now, right now we are not talking much about sectors, but this gives you the idea about the electricity generation in our country. Now with this 3,88,000 megawatt, what is the breakup? And this is also the latest figure coming from Ministry of Power. Very interesting to see. Let's see this. See the fossil fuel based electricity generation has got 60% component today. Out of the 100% here, 60% comes from the fossil fuel like coal, lignite, gas and diesel. And that is 2,34,000 megawatt. Non-fossil renewable energy sources, including small hydro, we have the contribution of almost around 37%. See? And if we include nuclear also into it, total non-fossil fuel is 39.6%. So it is almost 60-40 ratio. It's almost 60-40 ratio of fossil fuel and non-fossil fuel based electricity generation in India. Very interesting to see. But then, what do we want to do? We want to now increase the component of renewable energy into this generation, which is, as on today, it is 26%. If you see here, now wind, solar and other renewable energy sources contribute to 1 lakh megawatt electric power generated in India, and that is 26% of our total power generation capacity in India. So 26%, reasonably it's a good number, but government is now planning to increase this number, this percentage share of renewable energy, and a lot of new projects are also coming, and in coming days we will see this 26% will rise, and then it will go more and more further, maybe 28, 29, 32%, and so it is good. So in coming days we will see that this number will increase. This number will increase. This number will increase definitely. And then, so total non-fossil, as I said, 40%, fossil 60%. So this 60-40 should go other way now. 40-60. See what we want. We want fossil fuel say 40% and non-fossil fuel say 60%. But then it may not be possible very soon. It takes its own time. A large number of capacity addition is required for renewable energy. But then if this target is kept, say not 60-40 fossil non-fossil, but fossil non-fossil 40-60, then that will be a very desirable situation for our electric power generation capacity. Is it all right going on? Slides are visible properly. I see some noise here in between. Anybody wants to ask anything?
Because please mute yourself. Because
Yeah, my sincere request to all the participants that if there is no question from your side, you keep your mic in mute mode so that I can focus on my talk. But yes, definitely when if you would like to ask any question, you can unmute your mic and then you can ask question at any point of time during the lecture. No need to wait up to the last minute of the lecture, okay? So that we can interact also. Yes. So this is fine. Now this gives you a very clear idea. Why I am sharing this slide? Because if we are trying to understand the power electronics and microgrid, then also understand that what amount of energy level we are talking about. So right now we are talking about that 1 lakh megawatt power that is being generated through renewable sources, which is 26% of our total capacity. Now see here, electric power generation through renewable sources, and so that was the installed capacity, please understand. But now what is the power that we are generating? Oh, installed capacity is something different, and then what we are generating, again these figures I have taken from the annual report of 2019-20 Central Electricity Authority, Ministry of Power, Government of India. So these are also the real numbers published by our government. See, from 2014-15 up to 19-20, when we go and see the non-renewable energy sources generation in millions of units, you can see they are increasing, of course, and renewable energy generation is also increasing in millions of units. And then see, last year it was 1,38,000 million units, and total generation in million units. If you see here, so what is that percentage RE with respect to total generation? Percentage renewable with total generation. So this total is 13,89,000. If you see here, out of which only 1,38,000. So approximately 10% of electricity is generated using renewable energy. Approximately 10%. You can see here. Yes, of course, this percent is almost now doubling from 2014-15, where it was only 5.56%.
hello. Take one is hello. Sir, you are muted. Hello.
Okay, is it all right?
Yes, sir.
But
Yes,
when
sir.
I don't know at what moment it was muted, so that I can again repeat. I do not know at what time.
No, sir. Just a few seconds.
Oh,
There's no
is it?
issue.
Is it?
Yes, sir.
I
Yes,
don't
sir.
know, but because I was just presenting, suddenly it
No,
happened.
no. Just sir. Just a few seconds.
Fine, fine, fine.
Okay, sir.
So what I was saying is, uh, the generation capacity, if you see here, from 14-15 it was almost 5.5%, and now it is 10%. And you know, somebody will ask, okay, then if it is 1920 here we are seeing, how about 2021? So how about 2021? Any guess that what will be this number in 2021? And that also I have, it is 11%. I will show you that also. So definitely it is increasing. Let's go to the next slide. So does it make sense? You know, see here how our renewable energy picture is emerging out for India. Then source-wise breakup of cumulative renewable energy generation from April 19 to March 20. So the year 1920, 1,38,000 million units generated, and major contribution comes from wind energy. See here, 46.73%. Oh, the major contributor. And second major contributor is solar, that is 36.24%. See this, and it is also from the annual report of Central Electricity Authority 1920. I have mentioned references in almost each of these slides, so that once I share these slides with you, you can go to those references and learn more. It's my my approach, or my humble effort is that I want you to read these references further. So from the slide itself, you can find out the reference and go to that reference. You can easily download this from the Central Electricity Authority report website, and then read it further. So here you see the wind and solar are the major contributors, and then of course a small hydro, then here bagasse and biomass and some other sources. So finally, this is the complete 100% generation through renewable energy, 1,38,000 million unit, and that is hardly 10% of total electricity generated in India last year in 1920. So which are the major players? Wind and solar, that is emerging out very clearly. Okay, source wise breakup of RE capacity. Now this is March 2020, 87,000 megawatt capacity. Now source wise, if you see, wind has got 43% capacity, solar has got 39% capacity, and this is almost similar to previous one. They are contributing in generation based on their capacity. Exactly, see, they are contributing exactly based on their capacity. The numbers are almost matching. See here, this is the generation and this is the capacity. So definitely the wind has got highest capacity, 43%, solar 39%. They are almost now getting equal, coming neck to neck. Solar is taking over, I think gradually. We may see that solar is also becoming almost equal to wind capacity, and then both these sources will give power almost equal. Then other small hydro, biomass, and waste to energy. So this is the total, source wise installed capacity till March 2020. Okay, so India's RE sector at a glance, and here I was telling, see, in now 2021, how much? 11% of share, 11% of electricity is generated by, see, as I said, 1920 it was 9.95, that is of course the 10%. It is correct. And now in 2021, the total generation from all sources in billions of units, that was 1017 billion unit, and from that the renewable has got the share of 111 billion units, and that is 11%. 11%. And percentage share of RE in total installed capacity is 24%. See, so now one thing is to be understood, that RE has got percentage share of installed capacity 24%, but it is only producing percentage share in generation 11%. Can you see this? So share is only 11% in generation, whereas the capacity share is 24%. So we can still use our renewable plants on more optimal way so that we can extract more energy because they have a lot of capacity. But yes, many a times this capacity is not utilized fully because of several reasons, because of natural reasons, because of our limitations of the controllers, and because of power converter, their control limitation, many other limitations. But yes, we can still optimize it. We can extract maximum power and we can use them at fullest. So the capacity, because this energy are also intermittent. As I said, wind velocity changes, solar sun insolation level changes, temperature changes, and that's why we do not get continuous energy from these sources. But still 11% share is good in the RE generation, and we will see this number as the trend shows from 5% to 11% we have reached in last 7 years. So in coming 7 years also, if we work with the same or even more pace, it's not a wonder that we can reach up to almost 17%, 17, 18%. Yes. Good. So this is I have taken from the Ministry of New and Renewable Energy website, Government of India. It is annual report of MNRE 2020-21. See, this is from the annual report of MNRE, and that's why these figures are also authentic figures, the real figures issued by Ministry of New and Renewable Energy. So, any participant up to this particular point, know everything clear? Does it make sense? Now, have you got fairly good idea about RE capacity of India? Anybody? Why I am seeking the feedback? I would like to know that I am audible and the slides are visible. Is it going on okay?
Yes, sir. Yes, sir.
Okay, fine. So this is, I don't know, without this idea, you will not appreciate this entire workshop, because now you know at least that for what capacity we are working. Okay. Then see the solar potential. Annual report of MNRE says that there are 3 and 6, 7, 8, 9, 10, almost 10 states where the major contribution of solar comes. Even afterwards also this list is huge, like all our other states are also there, but their contribution is little less depending on the geographical regions and other things. So the maximum solar, you see the top 10 states in solar installation capacity in megawatt is on 31st December 2020. Karnataka has got the highest. Karnataka has got the highest, and that is how much? 7,300 megawatt. Then comes Rajasthan, 5,300. Tamil Nadu, 4,300. Telangana, 3,900. Gujarat, 3,900. Andhra Pradesh, Madhya Pradesh, Maharashtra, Uttar Pradesh, Punjab, and other states are also there in line here. So, see, these are the states from where we get the maximum solar energy. Their installed capacity is shown in megawatt by 2020. And in a similar way, wind power potential in India at 100 meters and 120 meters above ground level. And see, this is also from annual report of MNRE, Government of India, that our wind potential, now there are 7 windy states. This is very interesting. There are 7 windy states: Andhra Pradesh, Gujarat, Karnataka, Madhya Pradesh, Maharashtra, Rajasthan, and Tamil Nadu. And the wind power potential at 120 meters above the ground level is 68 gigawatt in Tamil Nadu, 127 gigawatt in Rajasthan, 142 gigawatt in Gujarat. So see, this is their potential. And Total 7 windy states. If you see wind power potential at 100 meter and 120 meter, so you have 651 gigawatt, and all other states including it is 43. So this is very less compared to the major 7 states here. This is by nature. This is natural. This is natural, depending on the geographical situation of our country. So this is by nature. So see here, the major contribution comes from the 7 states, and then finally total potential is 695 gigawatt. Oh, huge potential. So we can make use of this potential. See, the potential is there, it is to be tapped. Now energy is to be tapped. We need to tap this energy, and then we can significantly support our electricity demand through wind and solar. Okay, then comes here wind power installed capacity is on 31st December 2020. If you see, Andhra Pradesh has got 4,000 megawatt, Gujarat 8,000 megawatt, then Maharashtra 5,000 megawatt here, Tamil Nadu 9,400 seems to be the highest one in this chart. Yes, so Tamil Nadu has got maximum installed capacity of wind power. This is also from the MNRE Government of India report 2021 latest report. So we can see this contributing, and then others are all contributing 4 megawatt. So major states which are contributing here, 8, 9 states, you can see the major contribution, and total is 38,000 megawatt. But 38,000 megawatt is the installed capacity, and what is the potential? And that is 695 gigawatt. 695 gigawatt. See, so this is very interesting. And now I think with these 7, 8 slides, all the participants are very clear about the statistics of our renewable energy generation, renewable energy electricity generation. So I thought it is my duty to make you aware about the scenario of our country. Where are we standing, and where are we standing, and now where are we moving? So where are we moving? So this is, up till now we saw that where are we standing, and now where are we moving? So we are moving towards the 2022 electrical power targets, include achieving 175 gigawatt, and then it is revised as 227 gigawatt of energy from renewable sources. Oh, so this is what we want now. 227 gigawatt energy from renewable. So 100 gigawatt through solar, 60 gigawatt from wind, 10 gigawatt from biomass, and 5 gigawatt from small hydro. An additional 30 gigawatt from floating solar and offshore wind power. So see, now our targets are also set. And 227 gigawatt is a huge number. And now this much power, when you are getting from renewable sources, that is the fluctuating energy, you understand that how much complexity will come in the control of the grid now. That is the point which I wanted to emphasize. It is good that we are planning more and more contribution from the wind and solar. But at the same time, engineers' role, our role to control that power system is also increasing. And then this is the challenge for us, that how nicely we can design our converters, how nicely we can design our controllers, so that system is stable and system is optimized and giving us the maximum power from the green sources, whatever is available. So this is our plan. And that I have taken from National Wind Solar Hybrid Policy, Ministry of New and Renewable Energy, which was published in May 2018. See, so I am not just giving you some numbers here and there. These are all the real numbers taken from the proper reports issued by government. So this is what we understand now. Our plan is very clear, good. Now we come to our engineering. Focus on electricity generation through renewable energy sources. So hybrid, when I say hybrid power system, you have solar, you have wind, because these are the major players. You have generator here, and then you have battery bank here, because this energy is fluctuating energy, whereas here this is the one which we can, which can take care of stabilizing this energy, and at the same time we can pump the energy also wherever there is a large availability of energy, and then using proper conversion we can feed it to the load. This is very, very simple, but not that simple as it seems. Of course, it seems very simple, but this is simplified view. Real technological challenges are there inside. Okay, fine. Now here, where is the power electronic in electricity generation by wind, let us say. See, you have a windmill, wind turbine, generator, transformer, grid, distribution, and then load. Now in this load, grid, wind turbine, where is the role of power electronics? So the role of power electronics, if you see, it is here now. The wind energy conversion system is composed of several components that convert wind kinetic energy into electric energy in a controlled, reliable, and efficient manner. First of all, what energy we get? Kinetic energy. That is converted into mechanical energy. And mechanical energy is converted into electrical energy. And that electrical energy is also then processed in different forms, AC or DC, and then finally it is transmitted and then given to the consumer. So everywhere now power electronic will come into picture. So what is power electronic? Power electronic is a technology that deals with the conversion and control of electric power. See, very important. Conversion and control. So it's not only converting, it is controlling at the same time. So conversion of the power and control of electric power with high efficiency switching mode power semiconductor devices. Switching mode power semiconductor devices, when we say these devices are thyristors, GTOs, IGCTs, IGBTs, even MOSFETs. So these are the power switching devices where thyristor and GTO are high power devices. IGBT is a medium power device and MOSFET is a low power device. Are you getting it? This is very, very, simple and fact to be understood that high power devices are thyristors, GTOs, medium power devices are IGBT, sometimes IGCT also, and low power device like MOSFET. But MOSFET is the very high frequency switch. It can be switched at very high frequencies, whereas thyristors cannot be switched at those high frequencies. So if the power is large, then switching frequency goes down. Power is low, then switching frequency goes up. So this is, this is always a trade-off. This is always a trade-off. Okay, so we are not going into the depth of those semiconductor devices here. Then these applications include DC and AC power supplies, electromechanical processes, heating, lighting control, electronic welding, power line voltage, ampere reactive power compensation, harmonic compensation, high voltage HVDC, flexible AC transmission, photovoltaic fuel cell power conversion, high frequency heating, motor drives, and EV applications, electric applications. There are large number of applications of power electronics. Some are listed here, where our applications are also following. Our application means the topic of the particular workshop, that is our distributed generation and microgrid. So the 21st century is the golden age of power electronic applications. After the technology evolution stabilized in the later part of the past century with major innovation in power devices and digital signal processes. So here is your power converter. Here is your power converter, that is power semiconductor device. And here is your power controller, that is digital signal processor. So converter and control, and that is what I have written here, conversion and control. So who is the converter? That is the power switching devices. And who is the controller? The digital signal processor. Very, very fast controller. Very, very high power converters. This is what we want. This is what we want. So now you can see this picture. Then this gives you the idea about various applications and the nature of power electronics, where AC to AC, AC to DC, DC to AC, DC to DC, vice versa. Digital signal processor is the heart, and IGBT and thyristors, SCRs are the the switching devices. Whether it is a microgrid, HVDC or FETs, whether it is electric vehicle, whether it is solar MPPT, rooftop, whether it is motor control, drive, everywhere, whether it is control of light, illumination, heating application, many applications, everywhere, fan, blower, refrigerator, pump, drill machine, everywhere we can use this uh, power electronics. And then our main focus is right now here on the wind energy and here on the solar energy. We are not talking about EV or drives right now. Okay, fine. So we need the knowledge of solid state physics, where the solid state physics is nothing but our semiconductor devices, circuit theory, system and control theory, signal processing, electronics, electromagnetics, power system, electrical machines, simulation computing. So all this knowledge integrated, and then you can have one power electronic converter ready. That we must understand, that one power electronic converter demands knowledge of various fields which are shown here. Okay, so here we see now double-fed induction generator based wind energy conversion system. Well, this is a very complex system. It's not very simple system. So you have wind turbine control, you have the pitch angle control, then the gearbox, double-fed induction generator, and here is the grid. You have the transformer, 680 volt by 20 kV transformer, and on this double-fed induction generator from rotor, you have a back-to-back connected converter. See here. Now this is called back-to-back connected converter, where this is called rotor side converter. RSC, it is the rotor side converter. So this is rotor side converter, and this is, as this is grid here, this is grid side converter. This is grid side converter. So both the converters, an intermediate, there is a DC link because he is a huge DC capacitor sitting of the order of thousands of microfarad value. Now this is not a small capacitor. This is a big capacitor forming a stiff DC link here. So this is thousands of microfarad value capacitor, which gives you intermediate DC link. Now the rotor side converter and grid side converter both are operated using SPWM, space vector pulse width modulation. Sinusoidal pulse width modulation is also used, but nowadays in modern day controllers we use space vector pulse width modulation. So generally we say SVPWM, not only SPWM. SPWM is typically used for sinusoidal or sine triangle pulse width modulation, but I say we use now here SVPWM. Then you have the rotor side converter controller, grid side converter controller, and these are the feedback signals coming and you can see the bidirectional flow of current here because these are AC currents. So now this system shows that huge amount of power is being controlled in order to stabilize, in order to feed the stable power to the grid. Now the control is all lying here, that how are we controlling our converters, whether this is our inverter. Basically it is inverter because here is DC, here is AC, and then this is AC, this is DC, so it's converter. But if the energy flow is bidirectional, it doesn't matter. That's why the name is generally given here converter. I don't say that this is converter and this is inverter. Both are converter because both are bidirectional converters. Here you have IGBTs. IGBT is a bidirectional device because there is integral reverse conducting diode in it. You can see this. In every IGBT, there is integral reverse conducting diode. So these are, and that's why you see the current flow is in bidirectional. So these are bidirectional converters operated in order to control the voltage and frequency and the power which is supplied to the grid. And not only that, we are extracting maximum power also. See, this is MPPT. So you have the reference power here, and you try to operate this converter in such a way that you extract the maximum power from the wind turbine. And at the same time, now when you are connecting it to the grid, you have to see that this frequency, the frequency of this converter is synchronized with the grid frequency. So you have the frequency synchronization also working, coming into picture here. So active power, reactive power control, frequency control, frequency synchronization, then you have the maximum power point tracking. These are all the algorithms working inside this particular converter, and that is all done. So these are all your digital signal processors. Mind well, these are all digital signal processors, or FPGA, field programmable gate arrays. These are either FPGAs or DSPs. And here you have the drivers. These drivers are driving the IGBTs, and these are our converters. These are the sensors. These are the sensors to sense the current and to sense the voltage, and finally to extract the maximum power. So lot of control algorithms are working inside these converters. And simultaneously, even it is very difficult to focus on all these control algorithms. You have to see these algorithms one by one, whether you are focusing on MPPT algorithm, whether you are focusing on PLL algorithm, whether you are focusing on the control of grid side converter, whether you are focusing on the control of rotor side converter. So all these algorithms are separate, and then they are integrated finally, and then the entire system works. That's why I'm saying that now everywhere power electronics. Without power electronics, the wind energy and solar energy cannot be thought of. So this is the reference is also given here. I have taken it from the reference which is shown here. So it's back-to-back power electronic converter and rotor terminals on the operational behavior of the doubly fed induction generator wind energy conversion system.
Sir, uh, sir,
Yes,
can I interrupt? I have a small doubt which I want to ask you on the same subject.
please.
Sir, why is the carrier frequency of RSC is comparatively smaller than the carrier frequency of GSC?
Carrier frequency. You mean to say in
That
SPWM, okay?
yes,
Sine triangle pulse width modulation, there is a reference frequency and there is a carrier frequency.
yes, sir.
Please understand that here at the end of the particular converter, there is a huge capacitor sitting. So this frequency need not be that higher, because this is going to make this is working like a heavy filter. So this will make it almost pure DC. Whereas here what happens, there are very small inductors which are used here. If I use heavy inductors here, the system response will be sluggish. So here the carrier frequency is used little higher, because this dynamic response of this need to be higher, whereas this is the stiff link, so this dynamic response is not required that higher. And even if you go for higher carrier frequency, it will lead to higher switching losses. So in order to reduce the switching losses, we keep this switching frequencies little lower compared to this one, because by using high frequency switching here, we are reducing the size of the inductors, and we are making the dynamic response of this faster, where this takes care of the small switching frequency here with the reduced power losses also. And that is why sometimes this frequency is kept less compared to this carrier frequency. Getting it?
Thank you, sir. Thank you so much.
Yeah, okay. Dekho, please understand, I tell you one thing in general also. The switching frequency is switching frequency, I mean to say carrier frequency. Okay, in triangle, sine triangle pulse width modulation, the carrier frequency, switching frequency are same. But if you go to space vector pulse width modulation, switching frequency is half of the carrier frequency, because 1 over 2t is the fs. If you go into the details of that, sometime we can have that. So there the switching frequency is half the carrier frequency. It is good, because less is the switching frequency, less are the switching losses. But then the dynamic response and the fastness of the performance, it also demands the high switching frequency. So always while deciding the switching frequency of any converter, you have to make a trade-off between the performance of the wave shape and its dynamic response and the switching losses. Always there is a trade-off between these two, that the fast dynamic response and the performance of the current and the switching losses of the converter. Like for example, these are IGBTs. IGBTs can be used at relatively higher switching frequencies. But suppose I replace these IGBTs by GTOs, it can be replaced definitely, no problem, with their own driver circuits. But then I cannot switch the GTO circuit at that high switching frequency. So, but then I can have more power. So it all depends that whether you want more power, whether you want more flexible control. It all depends on the rating of this generator also. And that is why that what is the size of the windmill. That is also important. I am coming to that also in my some of the next slides. Let us see those things. So here, when I say this is a typical structure of a nanogrid. Now, nanogrid, again, it's a small microgrid only, but very simple. So you see here you have battery, you have PV, you have fuel cell, and then this one particular nanogrid. This is another AC nanogrid. You can have modules of these grids depending on your system. Then you have AC bus here. Why AC bus? Because these are the inverters. These are the inverters used. And then it is AC bus. Then you have other side, you have load. So AC to DC. Then DC to DC is also there. You can have the battery charging also here. Or other side also the power is coming. And then finally this is the AC bus. And then you can transmit it to the grid. So this is a very small system layout shown here. You may have varieties of sources at the input, but just one example is given. Now what I'm showing, you need a droop characteristic, because now voltage is controlled. आप देखिए ना, ये this is AC bus. So AC bus voltage is controlled, and then every generator has got its own droop characteristic. So see here, say DG1, DG2, distributed generator. So DC-DC converter, now here are our IGBTs, local controller, here local controller. Now there is a central controller also, and the role of central controller is very, very important. This central controller will see dual optimization algorithms are used here. And you have the internal communication also, low bandwidth communication between the central controller and optimized algorithm which are controlling the individual local controllers. Okay? I have just shown here only 2 DGs, but there may be more. And then that makes the system more complex, because each DG has got its own dynamics, its own natural conditions, its own capacity, and then its own cost also. and then how your central controller is extracting maximum power out of this. So large number of research problems are hidden inside it. Whether you are a power system engineer, whether you are a power electronic engineer, whether you are a control engineer, or even I say whether you are EC engineer, you need communication here, you need control here, you need power electronics here, and you need power system also here. So each engineering domain, our electrical engineering domain, is used here. Now, so here let's take one example. So one example is shown here where you have the point of common coupling which is shown here, PCC. So at this PCC, we would like to keep our voltage stable, but then there is power here and then frequency here. So you need to see that what is my stable frequency here and what is the reference frequency and how I can reduce the drooping characteristic and finally control my each and every converter so that the optimized power extraction takes place. So this is also one control problem, that how are you going to solve this control problem. You can apply classical control methods, or even you can apply nature driven control methods also. You can decide that what control algorithm you want to apply to this. See, for example, what is shown here, one simple case, that here is the minimum frequency, reference frequency, high frequency, and maximum frequency. So generally we want to operate it to this level. Okay, we want to operate it to this level. That is our reference frequency, and then this is the band given. Actually, this is the band. Frequency cannot be kept constant, but frequency will vary between this band. That's called F minimum and F high. But then it should not go to F max or even below F minimum. So the battery, PV, fuel cell, how you are controlling. So here, reduce the output power. Reduce the output power. Here, take the maximum power point. So mainly, this is the operational region in the as far as the frequency is concerned. And then you keep operating your PV, the fuel cell, and regulate the charging power according to the state of charge of the battery. So now so many control algorithms are working independently, and one control algorithm is also taking care of all these control algorithms centrally. देखिए ये बात है. This is how you. I am talking about a very simple example, but you may have more complex examples of your microgrid or the nanogrid. But then, what kind of conditions can be considered for study? Say battery and PV units operate together under adequate illumination. Adequate illumination is there, operate battery PV. Then battery and fuel cell units cooperate under extreme weather conditions, and the PV cannot output the power because extreme weather condition PV may not be able to sufficient, and then battery PV and fuel cell unit run together under insufficient illumination or heavy loading conditions. When loading condition increases, you have to operate all three. See, if you have the good illumination, operate the battery and PV. If you have medium one, then operate the battery and fuel cell. So it all depends that what kind of optimization you want from your microgrid. Very interesting. And this is the source also I have given you: variability, scalability, and stability of microgrids. It is the book edited by Fred Blaberge, published by IET in very recently 2019. So comparison between the conventional grid and microgrid. See the fact microgrid we sometimes call smart grid also. In general, in there is a large entity, smart grid is different. But here for our microgrid, even if you see, so conventional grid electromechanical, here it is digital control. Then one-way communication, you have two-way communication here. Centralized generation, distributed generation. Few sensors here, throughout sensors are to be used. Manual monitoring, this is in self-monitoring mode. Manual restoration, self-healing. Failure and blackouts, here is adaptive and islanding. So islanding operation is also possible here. Our microgrid can be operated either in the standalone mode or in the grid connected mode. So any fault comes here, islanding takes place, and islanding also, then it is seen that all the load which the microgrid is supporting, it should take power in a very stable manner. So the grid must supply stable power in the islanding mode to the loads also. These are critical loads. The limited control, here you have the pervasive control, few customer choices, you have many customer choices. So it all depends. Yeah, this I have taken from a book called Control and Optimization of Distributed Generation by Springer. So, well, I have given the references here almost in every slide so that you have good reading also. I am just helping you to find out better resources for your reading. So, few customer choices, many customer choices. The differences are very clear in the conventional grid and the microgrid. So, what are the classes of microgrid? Application type, if you see DC microgrid, hybrid DC AC microgrid, high frequency AC microgrid, line frequency AC, utility microgrid, commercial industrial microgrid, isolated microgrid. System structure wise, single stage power conversion or two stage power conversion. Supervisory control, that is centralized, decentralized, and distributed control. And connection of distributed energy resources. So electronically coupled or conventionally coupled. Electronically coupled means you have more flexibility and more control compared to the conventionally coupled systems. So types of microgrids are shown here, where everywhere you will find the converters, DC-DC converter, DC-AC converter, most of the time. So you must learn how to convert, how to control my DC-DC converter, how to control my DC-AC converter. For example, here, power electronic control has come now very evidently in this, that either it is PV, wind, microturbine, fuel cell, IC engine, battery group, whatever. My all different varieties of sources are here. Then AC-DC or DC-DC converters are here. Then DC-AC converter, output filter, and then it goes to the point of common coupling, where you have the area electric power system or local loads, and then monitoring is done and control is done. The control has got different levels of control also: primary control, secondary control, tertiary control, to control all these different algorithms running for different sources. But this is only a very simple block schematic shown that how power electronics has its role in the microgrid. So see, here is the converter and their control. Now each converter and each control is a specific topic on its own. Please understand. Am I going properly? Any doubt up to this point? Any participant? Any feedback, please?
Any questions, anyone?
Yeah. Please feel free if you want to even discuss anything, or even if you want to share your experience on this. If anybody has worked on microgrid, you can share your experiences also. It will help everybody. Okay, good. Let's move further. So here you see PV panel system, wind turbine, fuel cell, compressed air, and common AC bus is given here. Then utility grid, and then point of common coupling, static transfer switch. Static transfer switch role is very important during islanding operation, where a lot of sensors are there, and then system healthiness is being checked continuously, and then static transfer switch operates as per the algorithm. So this is a possible structure of a microgrid where you have distributed loads shown here. You may have the static transfer switch at several locations also, depending on the need of the system. So here, what kind of things? And now this is very important for all the control system engineers. That overview of the primary, secondary, and tertiary control building blocks. So now we have the converters inside, but say this is LV grid, this is our communication network, and this is distributed energy resource unit control. Now what is that? There is a primary control. We can see that power reliability, P and Q are controlled, voltage and frequency are controlled. So primary power, active power, reactive power. Then there is a secondary control also, where power quality is taken care of. And then the tertiary control is there where economics is taken care of. Economics plays a very vital role because utilities, they need to survive. They need to make money out of it. They need to uh, take care of their expenses also. So definitely economics plays a greater role here, sometimes greater than the quality of power also. Yeah, because so all the three controllers are now operating in proper communication. And then finally the power reliability, power quality and economics is taken care of. See, we can go into the depth and discuss about each and every controller, primary controller, secondary and tertiary controller. These are also distributed again, so the control is quite complex. Even controlling a small microgrid, it requires various levels of control, and that too the overall control. Then there is individual control of converter and inverter, and then the algorithms for MPPT and PLL are also there. So this gives you the holistic idea about how a microgrid is to be controlled. So the primary controller is used to provide reliable operation and to respond to communication failures. It is associated by frequency and voltage as inputs, and it gives control action that reactive power primary and active power primary to control the deviation of the voltage and frequency. Yes. The secondary control is used to regulate the voltage and frequency on the basis of its response to the load and supply changes. Its control action, that is P secondary and Q secondary, are given by calculation of the average of primary control actions. See, average of primary control actions. And then the tertiary control is used to improve the operation of the distributed energy resources units, so they have the optimal cost efficacy. Dekha? So optimal cost efficiency is very, very important. As far as the power limits allow the DER units to extend their power at equal marginal costs. Up to what limit, up to what extent you can extract power from that particular source, that is all decided by your tertiary control. Very, very important, and that gives you the cost effective solution. Large number of such energy management system softwares are available, and people write these algorithms, and then a lot of research is also being done in this area. You can choose some of your research topics from this area also: tertiary control and cost effective optimization of the DER in the distributed generation. So now, as far as inverter is concerned, at the grid side, if you see here, now here is our grid, and then this is DC link, stiff DC link, which I said, no, back to back connected converter, and then stiff DC link. So this is the intermediate link, and then inverter. These are the inductors and capacitor filters, and these are our Hall effect sensors. Whatever sensors are there, isolated sensors, and then analog to digital conversion is there. This digital signal processing and gate drivers. So inverter has got this control, and where the frequency is also controlled. So this will also take care of the synchronous phase lock loop system also. But this is a two-level grid connected inverter, which is having LCL filter. But this is a simple inverter which has not that much high power rating. But suppose you want high power rating, large amount of power to be controlled, then you have to go for multi-level inverters also here. And then this converter configuration, I mean to say converter is general name. Inverter configuration will be more and more complex, and their control also. So here inverter control, now you see the control is shown here. So you have the grid side, and then the solid line shows the power flow, where the dotted line shows the information flow. So lot of information flow takes place here. This is all kind of feedback, see, and then current and voltage feedback are taken, and DQ axis feedback is taken, PQ calculation and low pass filter, and then power controller. This is voltage control algorithm, current control algorithm, PWM inverter, filter, coupling inductor, and then finally it goes to the grid. And then you have the wireless communication also taking place here. Several signals are taken as feedback, and that is used to control the power. So overall, control of inverter is also complex, and then you need lot of control algorithms and the driving units to control the inverter, PWM inverter here. So inverter control, converter control, overall control, primary, secondary, tertiary control, these are all the main things where we need to contribute in a microgrid. So size of wind turbine, देखिए, this is what where the power electronics comes into picture. As I just said, that this is the one. Now suppose this power level is medium power level, then it is fine. But here the power level is very high, and then you need a megawatt of wind turbine. Then this kind of inverter may not be sufficient. Then you, because IGBT is a medium power device, it is not a high power device. And somebody say, okay, no, then I use thyristors, which are high power devices. But thyristor inverters require the commutation circuit, which is very, very bulky at that power level. So they are not preferred. But then IGCT is again a solution, which is nothing but the integrated gate commutated thyristor. So it is the GTO, gate turn off thyristor itself, with having the commutation circuitry integrated on it. Those devices are also used nowadays. So size of wind turbine, yes.
Excuse me, sir.
Yes,
Sir, I have one question.
please.
Sir, as the level increases,
Yeah.
DC-link capacitor voltage imbalancing occurs.
So
So what are the effects of DC-link capacitor imbalancing in the converter, sir?
yes, I understand your question. It is a good question. What happens that you said very correctly that if I go for multi-level inverters here in this one, definitely the here because for the sake of other participants also, what I want to say that here you see two capacitors, but this is a fictitious. This is the fictitious point. In two-level inverter, you don't need two separate DC sources. Only one capacitor is sufficient. But when you really go for multi-level inverter, then you have the large number of capacitors coming into picture here. Just a minute, I will have some water. Yeah, so in multi-level inverters, here you will have the large number of capacitors. Suppose that n level inverter, it requires n minus 1 DC link capacitors. So a 3-level inverter will require 2 capacitors. A 5-level inverter will require 4 capacitors. Now the point comes as the question is asked that what happens to this capacitor voltages? Yes, we need to balance this capacitor voltages through our PWM algorithms or separate mechanisms of buck boost converter or any other means. If the capacitor voltages on the DC link of multi-level inverter are not maintained equal, then there is the presence of lower order harmonics in the output of the inverter. So all those lower order harmonics will sit on this line, and these lower order harmonics are very difficult to be eliminated, and they distort the entire grid because here is your PCC, here is the PCC. So it's always important for us to maintain the DC link capacitor voltage balancing in multi-level inverter through varieties of techniques. Even my PhD work at IISc Bangalore was on DC link capacitor voltage balancing for multi-level inverters, 5-level and 9-level inverters. That itself is a huge topic. But my answer to this question is yes, capacitor imbalance produces the distortion with the lower order harmonics in the output voltage of inverter. It also produces unequal voltage stress on the switching devices. That is also not good. Some of the devices may fail because of the higher voltage stress on it. This is to be avoided. Otherwise, the quality of wave shape will not be good, and you will be introducing large amount of harmonics. And those harmonics even cannot be filtered by this LCL filter, because this is not designed for lower order harmonics. This is designed for higher order switching harmonics. That's why higher order harmonic filters are smaller in size. Whereas if you want to eliminate the lower order harmonics, you need bulky filters which will sluggish the dynamic performance of the system. So that is also a problem. So yes, harmonics, filter problem, the voltage imbalance on the devices, that is also a problem. So that is why DC link capacitor voltages of multi-level inverters are to be separately controlled in multi-level, and then it will add one more control algorithm into your system. Yeah. Is it clear? Am I giving?
Understood.
Yeah.
Yes, sir. Understood, sir. Thank you,
Yeah,
sir.
yeah. And but then there are many ways to control this DC link voltage also, which can be discussed separately.
Okay, sir.
But it is also one of the good topics. I say that if somebody would like to work on DC link voltage, DC link capacitor voltage balancing of multi-level grid connected inverters, that is also a good topic for research. So size of wind turbine, according to the aerodynamic properties, the power output of a wind turbine is proportional to the square of a rotor diameter and cubic of wind speed. देखिएगा ये very important है. Square of the rotor diameter and cubic of the wind speed. The large turbines can capture higher wind power with a lower installation and maintenance cost compared to the group of small turbines. देखा, इसीलिए we would like to go for larger and larger wind turbines having the diameter larger and larger. But the problem is that power who will handle, our electronic converter has to handle that power. So owing to this fact, the size of the commercial wind turbine has exponentially increased over past 30 years. Last 30 सालों में size of diameter of the wind turbine has exponentially increased. अब देखिए in 1980 the diameter was 15 meters and height was 24 meter. आज हमने जो बात की 120 मीटर पे बात कर रहे थे हम विंडी स्टेट्स में. सो now see the how it has increased the height as well as the diameter. This is height and then the diameter. So in 2020 if you see the power is 15 to 20 megawatt and the diameter, oh god, this diameter is almost it can in its radius accommodate a Boeing 747 aircraft. 145-meter diameter, 150-meter diameter. So huge windmills are there now, and then they can generate a lot of power, but this power is to be handled again by power electronic converters. There is the limitation. Reference is given. So the wind energy industry has gone through much technological advancement in terms of aerodynamic design, mechanical system, and generators, power electronic converters. Okay, so that's fine. Now kinetic energy to mechanical energy. You can see the internal part of one particular wind turbine. And then the wind kinetic energy is first converted into mechanical energy with the help of airfoil shaped rotor blades. Yes, the tower, nacelle and rotor hubs provide mechanical support to the rotor blade. The kinetic to mechanical energy conversion efficiency depends on many factors such as shape of the rotor blade, angle of blades, wind speed, velocity and air density. See, there are many factors. The wind velocity and direction are measured with the help of sensors, and a yaw drive is used to move the rotor blades along with nacelle towards the wind to extract the maximum possible energy. These are all mechanical things which I am not discussing much, but if interested, you can go through this. Then turbine run at very low speed, typically 6 to 20 rpm only. Multi-stage gearbox is used to couple the low-speed, high-torque wind turbine shaft. And for three-stage gearbox, the gear ratio usually vary between 60 and 120. Serious issues with gearbox. Now, gearbox has got its own issues. So, it's better to go for the gearless drive also. By matching the generator speed with the wind turbine speed, the need for the gearbox can be eliminated. Yes, that's possible. So omission of gearbox helps to overcome the aforementioned problems, especially in offshore wind turbines. On the other hand, the direct drive operation lead to some drawbacks in the design of generators, such as large diameter and more weight. Every system has got its own advantages, disadvantages. But then what we are doing here, the basic configurations. So you have different types of wind generators. Different types of wind generators available. Generator side harmonic filter is there. Then you have the power converter. Then grid side harmonic filter, step up transformer, and finally the grid. So this is how it works. So here our role of control will come, which will have feedbacks from both the side, generator side and the grid side. So these are the different generators used, as I just said: squirrel cage induction generator, wound rotor induction generator, doubly paid induction generator, permanent magnet synchronous generator, and wound rotor synchronous generator. That's fine. So the induction generator usually operates at high rotational speed, while the synchronous generator can operate at low, medium, or high speeds. So different comparisons are shown. That's fine. The generator output and the frequency change with respect to wind speed. So power electronic converter combine the electric generators to form a wide variety of WECS configurations, so wind energy conversion configurations. The switching harmonics are inevitable when using power electronics. That's why we need filters, because the devices are switching at high frequency. Harmonic filters are used in generator side as well as at grid side. Filter on the generator side converter reduce harmonic distortion in generator current and voltages. This leads to the reduction in the harmonic losses incurred in generator's magnetic core and winding. Filter at the grid side converter help to meet the strict harmonic requirements specified by the grid codes. Because grid side converter, you are connecting to the grid, so grid side code is to be followed, and that's why the filters are needed. The output of the grid side harmonic filter is connected to a three-phase grid through a step-up transformer, an electric switch gear, and a circuit breaker. So this is the complete wind energy conversion system. Then grid code requirements are there. I am not going to discuss grid code requirements, but some active power control, reactive power control, grid power quality, flicker, harmonic, fault right through capacity, and system protection. These are the main requirements for the grid code when you are connecting inverter to the grid. Ultimately, what all these things are to be taken care of by these things. See here, because where is the control? You have control here only. That's why it is so important that all the control burden will come on this inverter. And you can see now the system looking like this. अब यही तो सब है. This is all the complexity. So pitch control system for generator side power converter, control system for fault right through equipment, control system for grid side power converter, grid integration supervisory system, and coordination of different control system. This is the master control unit. So and now this is only one source. Now you are saying distributed generation. You have similarly the solar also. You have similarly the fuel cell also. You have the battery also. you have some other biomass source also. And then all this is to be integrated with the overall control. Source given. So representation of trends in high power wind energy conversion, gearbox, power converter, control, policies, grid codes. So why I am giving you this idea? Because from this one, anybody can identify the research area, and then you can find out the gap and make any one area as your research area. So classification of back-to-back connected converters in wind energy conversion system, a low voltage and medium voltage system. So two-level voltage source converter, parallel switches, parallel modules, current source converters, voltage source converters. Now series switches, three-level and four-level diode clamped inverter, three-level active NPC converter, and three-level, four-level flying capacitor converters. And then now here five-level cascaded H-bridge converters will also come. So either it is neutral point clamp converter like this, or it is flying capacitor converter, or it is H-bridge converter. So now multi-level converters are used in this wind energy conversion system, because each wind turbine is having megawatts of power in it, which a conventional two-level VSC cannot handle. अब इसका काम नहीं है. Now this cannot handle, so you have to go for this. This is the two-level conventional one, as I am saying. This two-level configuration. Okay, so that's fine, but then it has got the power limitation, and the switching frequency is 1 to 3 kilohertz only. Lower switching losses and high power density. DC link provides decoupling between generator grid. Generator transients do not appear on grid, so any transients here will not reflect here, because this is the DC filter sitting on this huge filter. Now what we are doing here, this is not multi-level, this is again two-level, but we are increasing the current capacity. These two switches are in parallel. You can see this. You can see these two switches are in parallel. These two switches are in parallel. These two switches are in parallel. So what we are doing, we are increasing the current handling capacity and ultimately the power handling capacity of the converters. This is the first alternative to multi-level inverters. Suppose you do not want to use multi-level inverter, you can go for this. This is the general trend followed by industry in order to increase the power handling capacity of the converter, because paralleling the IGBT is not the issue, but paralleling the thyristor is a big issue that you cannot do simply like this. So paralleling of IGBT is comparatively easy than the paralleling of the thyristors. So this easier approach can be followed. So this is two-level converter, as everybody knows. Then PWM technique, sine triangle pulse width modulation can be used, and unipolar or bipolar PWM techniques can be used. And then in this PWM, the fundamental is inside, and then fundamental component can be extracted, and other high frequency can be eliminated by the use of filters. So, but then if you go for multi-level inverters, the shape of the voltage waveform improves. So this is the shape of the waveform in two-level. Then say you go for three-level, then you go for a five-level. Then very nice wave shape is emerging out, and then output of the inverter itself is like a sine wave. So the requirement of filter goes down. Not only that, requirement of switching frequency also goes down. So small switching frequency, so low switching losses, less filter size, that means less sluggishness in the system, and better power handling capacity of the converter also. That is why multi-level inverter technology has now picked up. Now this is the one of that three-level neutral point clamp inverter. Now These switches are not in parallel. On the contrary, they are in series. So voltage rating is increased and then the power rating is increased. So this is the operation of the 3-level inverter, neutral point clamp inverter. And its different levels are shown here with the dark lines. The 3 levels are possible at a pole. And then combinedly, this is the 3-level inverter. And wave shape improves compared to the 2-level. So this is 2-level where voltage space phasor structure is shown as a hexagon, where there are 8 vectors possible, 2 zero vectors and 6 peripheral vectors, which are the active vectors. I will not go into the depth of this because this itself is a chapter. I mean to say a talk. Then you have multi-level inverter, so you have more number of voltage sources, and you have more resolution possible, so better sine wave can be generated. Then this is a 5-level voltage space phasor structure. So with the same DC link, now you have the finer and finer possibility of the AC waveform. So now you see this is the GTO based converter, 3-level inverter and 3-level converter, neutral point clamp, but use the GTO. GTO is the high power device. So it is better. 3-level inverter provides less dV by dt, so less electromagnetic interference and other advantages. Ideal configuration for wind farms which are in close proximity to substation, less than 5 kilometers. So now solar comes here because I wanted to give the idea about both. So the solar energy, this, that you have the array, the complete set of solar panels, and then DC-DC converter, DC-AC converter. So here is the model of the solar cell, single diode equivalent circuit. Then you have the IV PV characteristic. Everybody knows this side. There is nothing new. And then you have PV characteristic under different insolation conditions. So you always want to extract the maximum power. So MPPT algorithms are followed. So finally the scheme will be like this. Either you have buck boost converter, but here you see these converters are in cascade. How? This is the solar and this is the wind. And from there you have the 2 different converters, and then finally they are cascading here on the DC link. And then there is an inverter, and then finally it becomes a grid. So DC-DC converters and DC-AC converters. But limitations, buck boost and buck boost converters. Mainly the buck boost converters are used because entire load variation range comes here. And then this is the universal converter. Then maximum power point algorithms are there. Offline technique, online hill climbing techniques, artificial intelligence techniques. I was reading a paper where 17 different algorithms were discussed for the maximum power point tracking. So large number of people are working on such, whether it is perturb and observe method, or fractional open circuit or short circuit method, or it is hill climbing, that is incremental conductance method, or fuzzy logic or artificial neural or particle swarm optimization. Nature driven algorithms are also used, genetic algorithm. So but what are the challenges in MPPT? Sudden or ramp variation in ambient temperature and solar irradiance, sudden variation of load, partial shading, oscillations around MPP. So all these lacunas can be overcome by different techniques, and you can find out your own MPPT technique also. Then the grid integration is done by the PLL. So PLL is nothing but you are comparing 2 frequencies and generating the voltage, passing it through a low pass filter, and then giving it to the voltage controlled oscillator, that is voltage to frequency converter, and finally this frequency will match with this frequency. So that is a simple portion of PLL, but then it is complex to be implemented. There are several types of PLL schemes also available. So this is output characteristic of wind turbine, and then SPWM control is operated here. MPPT algorithm, this is for wind. So for both solar and wind you can operate MPPT algorithm, and then you can integrate them for VGS. So here you see grid side converter 1, and this is grid side converter 2. So this is converter 1, this is converter 2. And then finally here it goes to our output side. So this way you can operate the logics. Then standalone renewable energy sources. This is already discussed, but I am just showing some of the DC bus modular system and AC bus modular system. So DC bus and AC bus, you can see this is DC bus and here it is AC bus. It all depends that what kind of system you are working with. Okay. Then PV generation configuration systems are the centralized string, multi-string and AC modules. Different DC-DC and DC-AC converter topologies and their control. These are, nicely discussed in literature also. So multi-string converter technique, their advantages are discussed here. Then similarly, you have AC module technique and the modular grid connected PV generation system is better in industry. So suitable for cost-effective, large-scale standardized production. This is large-scale standardized production. This is the most suitable scheme. Modular grid connected PV generation. So dual inverter configuration for PV generation. Now dual inverter here, what is done that MPPT is okay. Now these inverters are operated at different frequencies. You can see one is operating at very high frequency, here it is very low frequency. So but finally when you cascade them you get a better wave shape. So this is better to be fed to the grid with lower harmonics. So you can phase disposition techniques are used here in three-phase inverters, and then you can operate them. One operates at low frequency, one at high frequency, and then switching losses can be reduced, but then the output voltage waveform is still improved. That's possible. In a similar way, now if you have more number of inverters, then output voltage wave shape can be further increased, improved. So 9-level inverter based grid connected solar system is also there. You have a 9-level inverter. This is the 9-level inverter configuration, this is the conventional one. But then now by turning this switch is on off, I can generate 9 different levels. So the quality of the output wave shape is more sinusoidal, less THD. And then you have the grid tied controller also. This is MPPT controller, which is for MPPT algorithm, which is here. See, this is the control switch. So this is used for maximum power point tracking of the solar array. And then this is used connected with the grid. And from this PI controller, the PWM is generated and given to all the 9 switches, S1 to S9, where S1 up to S4, then 5, 6, 7, 8, and 9. So these 9 switches are controlled in order to control the 9-level inverter. All these configurations, there are several such configurations available in their control. So this way, you have the there are multi-purpose converters also, and multi-purpose inverters also, multifunctional inverters also. Now the solar inverter can be used as a power quality compensator device also, like active filter, which I have shown here, or it can be used to compensate the reactive power also, because night time there is no power here. So if there is no power, it cannot be used as only inverter. But now I can use the same circuit, the converter, as power quality improvement, as active power filter. So it can help the grid by controlling the harmonics of the grid. So that is also advantage. So that is known as the multifunctional inverter in the solar system. So such kind of inverters are also available. I think there are that's why instantaneous power theory is used here. Instant active reactive power theory to operate this as active power filter. It's possible during nighttime conditions, so that it does not remain idle in nighttime, and then this investment is used. So this way there are varieties of things, and I think I should stop here because now this is the time. uh, I have covered almost the time allotted. Now here there is the time for the questions. So any of the participant, if you have any question, please let me know.
Thank you, sir. Any questions, anyone?
Yes, please ask if you have any point or if you want to discuss anything.
Sir, can I ask one question?
Yes, madam.
Sir, what are the recent technologies used in modular multi-level converters for enhancing the power quality during faults in the transmission?
Yeah. See, first of all, that we are using the uh, inverter. Now, what happens that in this inverter, the MPPT algorithm is also inbuilt, so that DC to DC converter can be eliminated first. So, if you are using the modular multi-level inverters, the grid side PLL and the input side MPPT algorithms can also be put into it, and you can reduce DC-DC converter, and also as they are multi-level and multi-modular, the modular fashion. So suppose any one of the solar cell is faulty, then also there is no problem. It can keep on giving you the lower voltage output, and then during maintenance the solar cell can be corrected that array, and then it can again restore the operation. So fault right through is also there. The output harmonics are also better because of the multi-level inverter, and then its dynamic response is very good. Low switching frequency operation because of multi-level, so the switching losses are also reduced. Nowadays the optimization techniques are also used in this one to extract the maximum power. So how the solar power can be extracted at maximum, we can apply the ANN techniques and other multi-point predictive control algorithms are also used depending on the pre-recorded natural conditions of the different days of the year. So there are so many advantages of this kind of multi-level modular converters for the solar system. Yes, somebody has some question here. Any other question?
Thank you, sir. Is there any other question? Anyone?
Yeah, ask if you have any question. But at the same time, see these modular multi-level inverters, their control is very complex. And there you have to use fast digital signal processors and sophisticated control algorithms to control the active power, reactive power, partial shading conditions, maximum power point, and also the islanding. If there is some fault at the grid level, how can we isolate our inverter? Otherwise, that inverter will also get overloaded and it will fail. So there are many control algorithms which are making this inverter really a multifunctional inverter. Yeah.
Thank you, sir. Thank you very much, sir, for sharing your knowledge in the field of power electronics present in an energy scenario and several research areas into this. It's pleasure hearing you, sir. Thank you, sir.
Okay, thank you. So with this, I take your leave. Thank you very much.
Thank you very much, sir.
Thank you, sir.
Okay.
Okay, I request all the participants to please go for break and we'll meet at 2:25 for another session. Thank you, everyone.
Am I audible? Manita ma'am? देखो आवाज आ रही है? Am I audible? Am I audible? Hello, hello. Hello? Hello? Am I audible?
हेलो
Ma'am, I'm audible?
हाँ यस मैम यू आर ऑडिबल
ओहो, मैम आपकी आवाज़ नहीं आ रही।
हेलो 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 आई एम ऑडिबल मैम
Am I audible, madam? Vanita ma'am? हेलो?
हेलो
हाँ मैम, अभी आई आवाज़। फिर से बोलो।
हेलो
हाँ, यस मैम आ रही है। ओके। आपको मेरी आ रही है ना?
हेलो
Ma'am, am I
आई एम
audible?
ऑडिबल
You are audible.
हेलो
आ रही? नहीं। बोलो तो आपको। हेलो? हेलो, हेलो? अब बताओ।
हाँ आप बोलो मैडम एक सेकंड
Now, ma'am, I'm audible.
हाँ
अभी? हेलो? हेलो? Now I'm audible, Vanita ma'am. Hello, ma'am. Hello. हाँ. Hello. 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 Yes, ma'am. हाँ. अभी आ रही है? Good afternoon all. We are waiting for our next session expert, so please wait for 2-3 more minutes. Good afternoon, sir. Good afternoon, sir.
Good afternoon. Can you hear me?
Yes, it is not very much clear.
Uh, okay, just a minute.
Sir, you can share your screen. Good afternoon, all. It is pleasure to introduce our next session expert, Mr. Yashpal Patel, sir. Mr. Yashpal Patel, sir, is Deputy General Manager, Research and Development Department at Hitachi Hyrule Power Electronics Private Limited. Mr. Yashpal Patel, sir, has completed the MSc in Electronics from Gujarat University. He is associated with many industries. He joined Hyrule Hitachi in 2005 and is having more than 15 years of R&D experience in the domain of power electronics converters. Sir, you can share your screen.
Yeah, just wait a minute. Can you see the screen?
No, sir, it's not visible.
You cannot see.
No, sir, it's not visible, sir.
Uh, can I share you the presentation?
Okay, sir.
I have shared you the presentation.
Okay, sir. Sir, where you have shared?
I have shared to your mail ID.
Uh,
Yes, Yashpatra, good afternoon, Vinita. Sir, your mail to me?
Yeah, I have mailed to you.
Okay, sir. I just checked. The mail is not received yet.
Can you recheck?
Yes, sir. I didn't receive. Yes, sir, I got. Yes,
Okay, can you share?
just wait, sir. I'll download.
Actually, I am not able to connect with my laptop, so I have connected with phone.
No issue. Yeah, sir, is it okay?
Yeah, it is okay. Okay, let us start.
Okay, fine.
Okay, good afternoon, all of you. So
Yeah, good afternoon.
today we will discuss about state of art technology for solar inverter. Basically, I am working in solar inverter with solar inverter since the last 10 years. So I just want to share some details about the solar inverter and what are the new things going in the market so that you people can understand the features of the solar inverter. Next page. So today we will cover this topic. One is I will give you the overview of solar inverter. Then we will discuss different types of solar inverters and what are the topologies for the power device used in solar inverter. What are the different features and meaning of that features in solar inverter? And also we'll discuss about the future technology. There are many advances happening in renewable energy that I will brief about that. Next is yeah. So now, what is solar inverter? I think nowadays everyone is much aware about what the solar inverter is. A solar inverter is basically a DC to AC converter device which convert the DC power of PV module and generate the AC voltage from the DC. And this AC voltage you can directly feed to the grid, or we can uh, supply to the local load. So this is the definition of the solar inverter. And now, for solar inverter, we have different types of solar inverter. Basically, one is what we called is grid-tied solar inverter, and another is a off-grid solar inverter. So what is mean by the grid type solar inverter? Grid type solar inverter means that in this case, the output of this inverter is directly connected to the grid. So whatever the power we receive from the PV module, that is converted to AC supply, and that is directly feed to the grid supply. So here we don't need to store the energy, and we can directly supply the DC power of the solar to the grid. Uh, and This type of solar inverter is very popular because the cost is very low, because you need a only single stage inverter for this, and also we can get very high efficiency because there is only single conversion stage. So that's why this nowadays, you whatever you will see, most of the time you will see the grid tied solar inverter. So whatever the people we are using as a rooftop inverter, or there are some commercial complexes, we see this solar panel, that is mostly grid tied inverters. Another is off grid inverter with battery backup. So here the output of this type of solar inverter is not connected to the grid. The PV power is converted to AC to supply to the local load. So it is uh, like a isolated area where grid is not available. In such area, you can use this type of off-grid solar inverter. So here the battery is charged when the excess power is available from the PV module, and the battery will discharge when the power is not available from the PV module. So this is a off-grid solar inverter. So nowadays, what we see mostly is a grid-tied solar inverter. So whatever we will discuss mostly will be related with grid-tied solar inverter only. Next page. This is just an overview of grid-tied solar inverter. Here you can see that there is a PV modules which is connected with the inverter, and that is connected with a transformer, and then it is connected to the grid. So this is a grid-tied solar inverter, and grid-tied solar inverter are less complex, and we have very less number of components, so make it cheaper. And nowadays, all the generation is going through through grid-tied solar inverter. Next page. And this is a block diagram for off-grid inverter. Here you can see that there is a battery connected with DC to DC converter. So here this is basically used for a local house which is situated at a remote location and where grid is not available. So this is a little bit costly due to the battery, because batteries are costly, and it is actually good for remote electrification where grid is not available. But where nowadays, I think most of India we have a grid available, so grid tied is most popular. Next. Here this is just a overview that how this solar power in India has increased. Means this is just a comparison. You can see that in 2009 there was a PV module cost that was 100 rupees per watt. So if you purchase a 300-watt module, then it is 300 into 100. That was the cost at in 2009. But due to government initiatives and due to improvement in the technologies and mass production of the PV modules, now this cost has reduced to like 20 rupees per watt. And due to this, we have also got the advantage in the unit. Means previously, if you consider, then if you want to generate a 1 unit of energy from solar inverter, you need you have to pay like 15 rupees. So that this was the charge that government was committing in old days, but nowadays that has been reduced to like 2.4 rupees per unit. So here we can see that where there is a drastical reduce in the price of the solar module, and due to that the cost of the electricity has been also remained constant for this long period of time, and we are able to generate a cheap electricity with the help of solar. Nowadays it is like comparable to, or it is better than thermal power plant, this the price which we have right now for the solar generation. And here the government initiative is also helping people. Our government has target for the renewable power is like 175 gigawatt by 2022 for India, but maybe this will not achieve. But this was our target, which was set by our government to have an initiative in renewable energy. Next. So now also in this grid tied solar inverter, it is like categorized in different types of inverter. Basically, it is just help to understand. One is string inverter. So string inverter, basically the range of this string inverter is up to 250 kilowatt capacity. String inverter means it is a small inverter, and there are three segments for this string inverter where the people are using this string inverter. One is residential, another is commercial and industrial, and third one is utility. So if you talk about residential, maybe all of you will be aware about that nowadays people are having a rooftop solar inverter. Basically that is come under the residential category, and in that we are using a string inverter. Another is commercial and industrial. So here small scale industry or large scale industry, they are making their own solar generation by putting PV modules on the roof or the space available with them. And third one is utility. Utility is basically a power producing company. So it is like a big setup is there, and they are in utility scale. They don't have any other activity, but their work is only to generate a power from solar. If we talk about residential segment, then the capacity of the inverter is ranging from 1 kilowatt to 6 kilowatt. So this is basically used for the rooftop solar inverter. And if we talk about commercial and industrial segment, the requirement is from 5 kilowatt to 100 kilowatt. So this is the requirement for the commercial complexes or commercial activity or industrial activities. And utility segment, the inverter range which is used is 50 kilowatt to 250 kilowatt. And if we see about advantage of string inverter, so string inverters are small in size, so it is easily replaceable. Cost is little bit high compared to central inverter. And now if we talk about central inverter, then the central inverter capacity is above 100 kilowatt, that we call as a central inverter. So nowadays we can have a central inverter in the range of like 2 megawatt, 3 megawatt. Nowadays some people have come up with 5 megawatt. So this so the central inverter means it is a single inverter having a very high capacity. It is highly reliable because if we consider a central inverter, then the number of parts which we use in central inverter will be definitely lesser compared to string inverter. So reliability is higher, cost is lower, because if we just compare 1:1, like if you want to make a 5 megawatt plant with a string inverter, then you will need like 20 numbers of string inverter, and whereas you need only one central inverter. So the cost of the central inverter will be definitely low compared to string inverters. And also in central inverter we have a good efficiency. It is about 98.4% euro efficiency. And the third category is micro inverter. But nowadays micro inverter is not so popular. Basically it was a concept like from small module you generate a power and you directly feed it to the grid but that concept has not worked well. So nowadays, the micro inverter, you will not able to see much. Next. This is just a overview of a string inverter and solar inverter. So in the given diagram, you can see that for string inverter, you have a PV modules and there are small inverters placed near to the PV module. So here you can see for string inverter, there will be multiple small inverters which will be used for grid tied inverter. And if we the next slide, you can see the central inverter. In central inverter, you can see that there are not small modules connected with the PV module, but there is only one big module, a big inverter, which is connected to the grid. So here you can see that in central inverter, we can just reduce the number of components, and maybe we can save good amount of cost. String inverter, like there are some advantage of string inverter also, that if you have a string inverter, then you will get the multiple MPPT. Multiple MPPT means each inverter will track the maximum power point of the PV generation. So you can generate a very good amount of power with the help of this multiple MPPT. Means if you have a shadow on one string, then also you can get a good power with help of string inverter. But if you have a shadow in the case of central inverter, then you will have a significant loss in the power. So one advantage of the string inverter is multiple MPPT, but on the other hand, it is a higher cost compared to central inverter. Third will be a little bit less reliable due to increase in the component. So this is the differences between the string inverter and central inverters. Next page. So this is a solar inverter topologies used for solar inverter. So basically, these are some of the topology which we can use. One is a two-level inverter, where you have to use IGBT of 1200 ampere. Another is NPC 3-level inverter. So here you can use a IGBT of 600 volt. This is we are talking about a 1000 volt system. So nowadays there are new technologies available. That is a 3-level ANPC 3-level with reverse series, and another is ANPC 3-level with RB IGBT, reverse blocking IGBT. So using this ANPC, we can have some advantage compared to 2-level and 3-level inverter. So here the losses are smaller compared to 3-level and 2-level inverter. And if we just talk about overall performance with ANPC, then we have a good advantage compared to 2-level and 3-level ANPC. But this is just a basic comparison. Next page. So we'll discuss some of the features of solar inverter. One of the important features of solar inverter is MPPT, that is maximum power point tracking. So what is maximum power point tracking? Maximum power point tracking is a technique used to maximize the power extraction under all conditions. So here you can see there is a curve, PV curve. This is an important curve. If you understand this curve, then you can understand what the MPPT is. So here on the x-axis you have a voltage, and on the y-axis you have a current. And on the current side you can see ISC. ISC means it is a short circuit current. So if you take a PV module and if you just short the output, you will get the maximum current, and that maximum current will be ISC, that is a short circuit current. And on the voltage scale, you can see that there is a VOC parameter. There is a VOC point. This VOC point means when you don't have any connection, means your PV panel is isolated and it is not connected to anything, and you just measure the voltage across the PV module, you will get the VOC voltage. That is the VOC voltage. But what is the power? Power is a multiplication of voltage and current. So if you just see the point VOC, so at a VOC we have a higher voltage, but we don't have any current. So here the power, if you see, there is a power curve is also there. So you can see a power curve which is in blue line. So at VOC location, you can see that the power is zero because current is zero, voltage is available. So V into I, it will be zero. And if you see at the location ISC, then here also there is a same issue that you have a maximum current, but voltage is zero. So the power is zero. And now you can see that Pmax point. So this Pmax point is a point where your multiplication of V into I is maximum. This means that we have to operate the PV module at such a voltage that you can extract the maximum power from them. Means if we load the PV module such a way that the voltage of the PV module became VMPP, and at that time you have a maximum current. So due to that, you can get the maximum power. So this is why it is needed to have a maximum power point tracking. So all the solar inverter will try to track this maximum power so that we can get the maximum benefit of PV power available with the module. Next. Why this maximum power point tracking is needed is if the VMPP is fixed, means if the voltage of VMPP is fixed, then we can have we don't need a maximum power point tracking, but we can just set our inverter at fixed voltage reference. But that is not the case with PV module, because if we see the PV modules, the characteristic is changing with the temperature and the radiation. So basically this graph shows you that this is the IV characteristic of a module with a different insulation level. Means if the radiation is different, you can see that the PV curve has a different characteristic. Means if the the radiation is 200 watt per meter square, then the short circuit current is at some different level, and if you see at 1000, then the short circuit current is at different level. So on the next side, that figure B, you can see that it is a PV characteristic of the module at different insulation level. Here there is one line, you can see that orange line is there. Basically it is a maximum power point, but you can see that it is continuously varying. Means based on the radiation, there will be constant change in this point. So due to that, we have to track. And if you see that C curve, that is a PV characteristic of the module at different temperature value. Means if the module temperature changes, then also this VMPP, that maximum power point, will change. So in D curve, you can see that that orange line is there, which is tracking the maximum power point, but you can see that this point is continuously varying with the temperature. So from this we can understand that the maximum power point tracking is required because due to change in the conditions of radiation and temperature, there is a vast change in the MPPT point, and due to that we need a constant tracking of maximum power. Next. So these are the common method used for MPPT tracking. One is perturb and observe. So in this method, the controller adjusts the voltage by small amount and check the power If the power increases, the controller continues to adjust voltage in that direction and try until the power no longer increase. It is a simple logic. So basically in this method, what the controller will do is controller will start from the VOC. So it will set the reference at VOC, and at VOC, as we know that the power will be 0, and slowly it will try to change the voltage and it will check the power. So every time it will change the voltage and it will check the power. So if the direction of the change in the voltage is correct and we are getting more power, then it will continue in that way. Otherwise it will operate on the opposite direction. So this way it will try to track the maximum power. Another is incremental conduction method. This is also one of the method to track the maximum power point. So here there will be incremental change in PV current and voltage, and it is used to predict the effect of the change in voltage. Here this method is not mostly used because it is more computation is needed and it is little bit complex. Next, now one of the other features of the solar inverter, if you go through, is LVRT. So what is LVRT? LVRT is a full form is a low voltage ride through. So basically this LVRT requirement is not for a small scale solar inverter, but it is needed when you have a big solar inverter and you have a big power plant for generating a solar power. So what is LVRT? So it is the ability of the inverter to stay connected to the grid throughout a small or medium dip. So normally what will happen that when your solar inverter is connected with the grid, sometimes what will happen that due to some voltage dip in the grid, there will be a very huge dip in the voltage, but maybe this dip should be a small duration or long duration. But if it is a small duration dip, then inverter should remain connected with the grid, and it has to support the grid. So why this features is required for large solar power plant? Because in older days there was solar inverter and wind turbines, wind inverter. They used to shut down during this grid abnormal condition. So if there is a voltage dip, what will happen that in the olden days this solar inverter and wind turbine turns off. But what will happen that if you have a very good amount of power generated from solar and wind. Now if we consider a present scenario that now we have an increase in the solar power generation and wind power generation. So now we have a good amount of renewable energy connected with the normal grid. But if due to some way, if there is a dip in the grid, and if this solar power and wind power generation, wind power plant, if they turned off, then what will happen that there will be a overload on the grid and it can result in the collapse of the grid. So in order to avoid this situation, now this LVRT feature is made compulsory for this large power plant using a solar and wind generation. So another during LVRT, one more features solar inverter will do is whenever there is a dip in the grid voltage, inverter will try to feed the reactive power to the grid. So with the help of that, what will happen that it will support the grid, and if there is a small dip, then we don't need to disconnect the inverter, and it will avoid the condition where the grid can collapse. So here below graph is a graph for the LVRT. I mean, so what is a LVRT graph? So this different countries has a different grid code and different requirement for the grid. So here you can see that x-axis is a time scale and y-axis is a voltage in percentage, voltage percentage of rated voltage. For example, if you have a 90% voltage, I mean, if your voltage has reduced to 90%, then there is no need to disconnect and inverter can continue to operation. But if if our grid voltage is at 85%, then at least inverter should connected with the grid for 3 seconds. So it is 300 millisecond, means 3 seconds. So inverter has to connected with the grid for 3 seconds. At least it should be connected with the grid. Means it should not be that if there is a dip of 85%, then you should disconnect your inverter. Your inverter should continue to operate and for at least 3 seconds. If this voltage doesn't stable, then you can disconnect. And during this period, you have to generate a reactive power to support the grid. Same way, you can see that if it is a 15%, means if our voltage of the grid is reduced to 15%, then we have to connect it with the grid for 300 millisecond, and we have to generate a reactive power to support the grid. Okay, next. So this is something. This is our practical result I am sharing with you. We have performed this LVRT at our factory, and we have got the below result. Here you can see that first graph is a voltage where our voltage was 350 volt, and there was a dip in our voltage. So this dip we have generated purposefully at our factory end, and you can see that the voltage has reduced for like 300 millisecond. And during that moment, you can see that current. Basically, this current is a reactive current which we are feeding to the grid to support the grid. So third one is a percentage of voltage versus reactive current. So you can see that whenever there was a dip, our inverter has feed a reactive power to support the grid. So this is a very important features for this solar inverter, because when you have a more and more generation with solar power plant and you don't have these features, then there is a chance when a national grid can collapse due to just this unavailability of this feature. Next. Similarly, for there is a low voltage ride through. Similarly, there is a high voltage ride through feature. So in this situation, the solar inverter should stay connected to the grid in the condition of the high voltage on the grid for a short time. Means if there is a short duration, if there is a surge in the voltage, then you should not disconnect it immediately, but there is a certain time mentioned by our standard. You have to connect with the grid, you have to remain connected with the grid for that amount of time. After that, if it is a continuous over voltage, then you can disconnect. So here you can see that if the grid voltage is 130%, then you have to instantly disconnect our inverter from the grid. But if it is between 120% to 130%, then you have to remain connected with the grid for 0.2 second. And if the grid voltage is 110% to 120%, then you have to stay connected with the grid for 2 seconds. And if it is within 10%, then you have to continuously connected with the grid. So this is a high voltage ride through feature is also helpful for the grid stability. Another feature is a frequency ride through. Similarly, if there is a change in the voltage, you have to connect it with the grid. You have to remain connected with the grid. Similarly, it is for the frequency ride through. In this situation, if there is a change in the frequency, then you have to stay connected with the grid, and we have to continue to the feed to active power for the predefined time. So basically, our standard frequency we can see is a 50 hertz. So that is our standard frequency. So as per our standard, means if the frequency is above 50.5, then you have to reduce the active power generation, because when this frequency increase, it means that the generation capacity is higher, and the demand on the grid side is lower, means the load connected to the grid is has a lower capacity, and whatever the power we are generating is higher. So what we have to do is we have to limit our active power. We don't have to feed the active power. We have to limit our active power according to there is a graph is available. I have not mentioned that graph in this presentation, but we have to stay connected with we have to reduce our active power generation according to that graph if the frequency is higher. If the frequency is lower, then also we have to continue to generate continue with the grid connection up to certain time that is mentioned in the standard. Next, one more feature of solar inverter is islanding protection. Maybe someone of you are aware, or maybe you are not aware. This is the islanding protection. What is islanding protection basically is, so whenever if someone disconnect the grid, you can see this below drawing. There is a breaker that is mentioned, and this breaker on one side it is connected with the PV inverter and load, and on the another side it is connected with the grid and load. So normally what should happen, that whenever you open this breaker, the inverter should stop generating the power. But what can happen is, basically grid tied inverter is taking the voltage reference from the grid. So even if you disconnect the high voltage, if you disconnect from the grid, PV power is available. If the PV power is available and the load requirement is lesser than the PV power available, then it may happen that the inverter will continue to generate the power. Means someone has turned off the breaker, but still the power is available at the inverter and transformer end. And if someone if there is some person who has deliberately turned off the breaker for the maintenance purpose, he will not know that there is a power is still available at the transformer end, because what he will think that he has disconnected the grid, so there should not be any power available near to the load one. But due to solar inverter, that there is a possibility that power will continue at that moment, that end. So due to that, there is a islanding protection is must. So what islanding protection is, we have to detect that there is a disconnection of the grid, and we have to turn off the inverter. So this is basically a safety features. So if we don't follow this safety, then there is a chance of a risk that the service person for the grid can have a shock, electric shock. Next. So basically, there are different methods for detection of islanding. So normally, there are chances that whenever this type of situation occurs, that whenever there is a disconnection of the grid, normally it will happen that the load which is connected to the PV power will be very high, and with PV inverter will be very high. And what will happen that inverter will observe under voltage or over voltage condition, and it will trip. So this is a passive islanding method. One of the passive islanding method, we detect under voltage and over voltage situation at the grid end, and if the such situation occur, we should turn off the inverter in 1 minute, in 2-second time. And similarly, if there is such a condition occur, sometimes we can detect under frequency and over frequency also. And sometimes we can detect the rate of change of frequency and rate of change of voltage, because whenever such an event occurs that you disconnect the grid from the PV inverter, you can see that there will be change in the voltage, there will be change in the frequency. So you can detect all this item and you can turn off the inverter within 2 seconds. But sometimes what will happen that if the load is smaller compared to whatever the PV power is available, what will happen that inverter will take the reference from their own grid and it will continue to feed the power. So in this situation, we may not detect this above passive condition, that under voltage or over voltage. So in such situation, we have another method, that is an active method to detect islanding detection. So in this, what we can do is we can generate some specific amount of harmonics. We can inject specific amount of harmonics in the grid, and we will continue to check this harmonic. If our inverter is connected with the grid, then this harmonics will be observed by the grid, and you cannot see any harmonics at the inverter end. So this is one of the method through which we can detect active islanding. If the grid is disconnected, then what you will see is you will observe the harmonics at the inverter end, and you can detect that grid is disconnected, so you can disconnect your inverter. So this is also one of the important safety features for solar inverter, and it should be compulsory to have these features in our inverter in order to have a safety for the maintenance person. Next. There are other features, other requirement of solar inverters. One is a dynamic reactive power support. So what is this? So whenever your inverter is connected with the grid, this is basically required for a big power plant, not for a smaller rooftop inverter, but whenever there is a big power plant. So what it will do is it will continuously observe the voltage situation at the grid end, and if the voltage is higher, it will if the grid voltage is higher, it will draw the reactive power from the grid. So if we draw the reactive power from the grid, the voltage will reduce a slight. And if the voltage is reduced at the grid end, what inverter will do, inverter will try to inject the reactive power to the grid to support the voltage. So by this injecting reactive power or consuming reactive power from the grid, what we can do is we can stabilize the grid voltage. So we can have a better grid stability with these features. Nighttime reactive power support. So similarly, what we are doing in daytime, we are dynamically supporting the grid with reactive power. So nighttime also we are supporting the grid with nighttime reactive power. So what we will do is there are two requirements for this nighttime reactive power. One is that whenever this solar power plant is there, you have a in daytime there is no issue because solar is generating a power, but during the night time there will be a transformer and other load will be there. So what will happen that during night time the solar power plant will demand reactive power, and if your power plant demands reactive power, then the government can impose some penalty on you. So in order to avoid this penalty, what inverter will do is inverter will operate during the night situation, and inverter will inject reactive power to the grid according to the requirement of the power plant. So with the help of this nighttime reactive power features, we can have a unity power factor at the grid level during the night condition. And then another is nighttime fault ride through. So whatever we have seen above, that low voltage ride through feature, high voltage ride through feature, the same features can be given during the night situation also. Then another is PV insulation monitoring. So if you see a power plant, then you have a multiple cables which is connected with the multiple panels, and then PV modules. There are many PV modules connected in the power plant. So there are chances that over the time this cables can get damaged, and its insulation get poor. So one of the features required in solar inverter is to continuously monitor the insulation of the wire. Means basically what we are doing here is we are measuring the resistance between the ground and the positive and negative terminal of the PV power. So by that way, we can just check the insulation situation of the cable. So if there is a deterioration in the cable, then there can be an alarm on the inverter, by which this alarm, the plant operator can understand that there is some issue in the cable. So he can check the cable, and if there is a faulty cable, he can replace the faulty cable. Same is ground fault detection. So there are possibility that sometimes that PV cables can get break due to handling or some other issues, or maybe some rat or some insect cut the cable. So in such situation, we have to detect this ground fault situation, so that the customer or plant operator can understand that there is a issue in the cable and he can replace the cable. Another is string current monitoring. So basically the string current monitoring is when you have a big central inverter where you need to have a multiple inputs connected from the PV plant to the inverter, and you have to monitor the string current. Means there are multiple string will be connected in parallel, so you have to monitor a string current, so that if there is any issue in particular string, you can understand that this string is not generating a power, so you can check that string. So this is also one of the features for solar inverter. Next. Now a feature technology in solar inverter. So nowadays there is an intelligent monitoring of the inverter with IoT. So basically in these features, what we can do is, means if you have a mobile and you have a smartphone application, you can just download the software of a solar inverter, and you can monitor the parameter and status of the solar inverter on a smartphone. Means wherever you go. So there is a small device which is connected with the inverter. So that inverter is connected with the Wi-Fi, and then this data is sent to the internet over the internet, and you can access the you can just monitor the parameter of the inverter wherever you are. If you have internet available, you can easily check the status of the inverter. If there is any issue, you can just inform someone to rectify it. Another is use of silicon carbide IGBT instead of conventional silicon. So normally we are using a silicon IGBT normally, but nowadays we can see that silicon carbide IGBTs are also coming. So basically some of the features of this silicon carbide IGBT is They can operate at higher switching speed, and they can operate at higher operating temperature. But still, the price of the silicon carbide is higher compared to conventional inverter. So, with help of higher switching frequency, what we can do is we can reduce the filter size. So, for solar inverter, we need a LC filter. Basically, it is an inductor and capacitor filter. So, if you operate at a higher switching frequency, then you can reduce the size of this filter. So this is one of the advantage of silicon carbide IGBT, but still the cost of the silicon carbide IGBTs are very high, and so it is not so popular for solar inverter. But if the costing can reduce, then in the future it can happen that this can be this silicon carbide IGBT can be more popular in future. Next. Another is the 1500 volt DC. So in older days, up to 2017, the solar power plant was operating below 1000 volt DC. So the maximum DC voltage of the PV module was up to 1000 volt DC. But nowadays, we have a 1500 volt DC. PV modules are available. So basically, it is not a for a single module, it is 1500 volt DC, but you can series number of PV modules, and you can have a up to 1500 volt DC. So now the inverter has to operate at 1500 volt DC. So what will happen that with 1500 volt DC, if you with 1000 volt DC and 1500 volt DC, the big advantage is that with the increase in the DC voltage, you can reduce the current. Now we have increased the voltage, so we can reduce the current. And when you reduce the current, what will happen that the cable which is used for transporting PV energy from PV module to inverter, there is a huge cost of this cable, and we can reduce the cost of this cable with having this 1500 volt DC solar inverter. So nowadays, if you just consider most of the power plant manufacturer, power plant people, so power plant people are preferring 1500 volt DC solar inverter in the place of 1000 volt DC string solar inverter, because in this 1500 volt DC we can have an advantage of saving in cables, or we can have some saving in transformer. So basically it is a benefit to all the people. So it is now most preferred compared to 1000 volt DC string inverter. But still, if you talk about small system like commercial segment, or you can, if you say about rooftop segment, here it is operating on the lower voltage. It is not operating on the higher voltage. This 1500 volt DC is just for big power plant. Next. Then nowadays, one of the, maybe you may have heard that energy storage system. This is basically required because if you see the solar energy, so solar energy is available only during the daytime, means during the night time you don't have a solar energy. And below you can see the typical load pattern for the Indian grid. Here, sorry, this graph is not good, but here x-axis is the time in 24 hours. So basically it starts from 0 to 24 hours. So here you can see that during morning condition, like up to 5 or 6 a.m., the energy requirement or the power requirement is almost near to 0. But as soon as the day start, like 6 a.m., so 6 a.m. to 5 or 6 a.m., you can see that it is a steady power requirement is there. But if you see that between between 6 to 8 a.m., 8 p.m., there is a surge in power. Means the demand of the power is suddenly increased because people will start using the lamps, light will turn on, some of the factory will be still running. So there is a huge peak during that period of time. And as soon as the night will increase, night will come, and due to night situation, people will turn off and go to sleep. Then again, the power will reduce. So here now there is a problem that in the daytime you have a steady power. There you can use your solar inverter. But during the night situation, like between 6 p.m. to like 8 or 9 p.m., where you need a very high power, means the demand of the grid is increasing suddenly. So if by some way, if we charge the batteries during the normal generation, and if we use that power during the night situation, then we can reduce the burden on the grid, and also we can reduce the dependency on the thermal power plant. Next slide. So here you can see that this above graph is there. One is time hours and another is load. You can see that the red line is showing the load demand, means it is the demand of the grid, and a blue line is a solar generation. So basically what we can do is when we have excess solar power available, we can charge the battery, or we can store this energy during the daytime. And if we can provide this energy, the stored energy, we can release during the evening situation when the demand is very high. So with this way, you can reduce the capacity of thermal power plant. Means you can build more and more solar power plant without worrying about the grid stability. So here you can see the below diagram where PV module is there, solar inverter is there, transformer is there. So along with this solar inverter, one battery inverter is also connected, and it is connected to battery bank and transformer. So what will happen that during the daytime, this battery will be charged, and during the evening time, when there is a peak demand is there, during that time, this battery inverter will feed the power to the grid. So during daytime, solar will give the power, and some of the power will go to the grid supply, and some of the power will be used for the charging of the battery. And during the evening time, it will be feed to the grid. So by this way, you can have more stability on the grid side. Next. This above battery energy storage system, this can help us in different ways. Not just it will just provide the power during the peak demand, but it can also help for a frequency regulation. So as we discussed during above slide, that we have a fold or ride through features. So here, if there is any change in the frequency, means here you can see that there is a graph is there. One end is frequency, and another axis is time. So you can see that whenever this frequency of the grid will be higher than 50.02 hertz. This means that we have excess power on the grid. Means if the frequency is higher, this means the demand is less and generation is more. So this is the time where we can charge the battery. So this energy storage system can charge this battery during this hour, and if our grid frequency is below 49.98, then it means that the demand on the grid is higher and generation capacity is lower. So here we can discharge the battery. So with the help of this action, what we can do is we can have a more stabilized frequency on the grid side. So this is one of the benefit to use energy storage system. Next page. So in previous slide, I have mentioned that it is a battery and inverter, but it should not be always battery. Means nowadays people are thinking on different method for the energy storage. So energy storage cannot be with always battery, but there can be other means to store the energy. First one you can see is gravitational, which is a mechanical. So it is a pump storage. Basically what here we can do is whenever we have to charge, we have to store the energy. What we can do is we can use the pump and we can store, we can pump the water to higher altitude. So if we store at higher altitude, we can release that water again to generate the energy. So this is one way to generate, store the energy and use that energy whenever it is required. But this pump storage, basically it is very big and you need very big space, but it has also advantage that the storage capacity can be very huge. You can store for a longer period of time. Same way it is a flyback is another energy. Another is thermodynamics. So in this situation, the energy is stored in heat. So whatever the energy we are energy is available from the PV power plant, that can be stored as a molten salt. So basically it will stored as a heat source, heat, and whenever the heat release, it can again generate the electricity, and that we can use back. Another is battery, which is like there are different types of battery available: lead acid, nickel cadmium, lithium ion, nickel hydride. So there are different batteries. So this is also storage method. Another is electrochemical. So the flow cell. So nowadays this flow cell is also popular to store the energy. So for energy storage, people are using this method also. Another is hydrogen and fuel cell. So basically in hydrogen cell, you can say that whenever we have excess power available on the grid, we can use that power to have electrolysis, and we can separate hydrogen and oxygen. And whenever we need to generate energy, we can combine this hydrogen and oxygen to generate electricity. So these are the different storage methods. Another is electric supercapacitor, and so these are the different method which can be used for the storage of energy. So nowadays there is a we are seeing that in near future there will be a very huge demand for this energy storage system, so that we can have more and more solar inverters generating in the field. Okay, next. Okay, thank you. If you have any question, you can just ask me. If you don't understand anything, you can just ask me so I can again explain to you.
Thank you, sir. I have one question.
Yeah.
Sir, in one of the slides, you have shown that when fault occurs in the system due to heavy current, inverter trips. And at that
Yes.
moment of time, reactive power support is provided in the system.
Yes.
Can you please explain this, sir? Because I think when inverter trips, that reactive power is provided by the inverter itself, I think so. So how it is provided by the inverter if inverter trips at that moment of time when fault
Okay.
occurs?
Okay. You are talking about that graph which I have showed, that voltage, current, and
That yes, sir. That reactive power, and you
okay,
have shown
I
that.
think slide number 15, page number.
Yes, sir. This one.
Okay. So here basically there is a dip in the voltage. So you can see that normal voltage was a normal. It was around 350 volt, and then there was a dip in the voltage. So during this deep situation, what inverter should do is inverter has to feed the reactive power. This is not an active current. Means the second graph is current waveform. So this is not an active current, but there is a reactive current which we feed to the grid. So with the help of this reactive current, what will happen? The grid voltage will increase and it can support the grid for this duration. So what was your question?
So that's it. Just I want to understand this concept that when the inverter trips, at that time
Yeah.
the reactive current that which is shown by this red waveform.
Yeah.
So I just want to clear this that at the when inverter trips, at that time that reactive support is provided by the inverter, right?
No, actually here inverter is not tripping. Inverter is continuously operating.
It is operating, sir. Okay.
Yeah, there is just a dip in the voltage. So
Okay.
what inverter should do, inverter should not disconnect from the grid. Inverter should feed the reactive power for the
Okay.
same time. Means if it is a dip of like up to 15%, then you have to, for 300 millisecond, you have to provide this reactive power. Means if this condition continues for a longer period, then you can disconnect the inverter. Then there will be no reactive power.
Okay. Okay.
But if it is for a short duration, then you have to support the grid.
One more question based on this also, sir. Like voltage dip occurs when the fault occur in the system for this duration of time. At that time,
Yeah.
THD will be reduced, right?
Which
So
THD?
THD, yes, sir.
Yeah.
So at that time, the THD is reduced. Is there any method through which we can improve this THD during this time when fault occurs?
Whenever this fault occur, actually our main purpose is there should not be failure of the grid.
Yes, sir.
So
Okay.
maybe that at that moment THD is not important, but supporting the grid is more important.
Okay. So, sir, power quality, that means if it is poor at for certain duration of time, that will be okay. But the most important thing is to provide the reactive support,
Yes,
right,
yes.
sir?
Because what will happen that
Okay.
if you have a like say like you have a 50% power generation from thermal power plant and 50% power generation from solar power plant,
Yes.
and if there is a very huge deep means there is a some sudden short circuit or some condition arise, and if our inverter means solar power plant inverter trips, what will happen that this thermal power plant which has only 50% capacity will get overloaded and it will also trip. So what will happen, basically it will collapse the grid.
Yes, sir.
So it will collapse the grid. So we have to avoid such situation. So if there is a temporary dip, then we have to support the grid. If it is a long dip, then you can disconnect.
Okay. Okay. Thank you, sir. Is there any other question? Anyone? Any question? Anyone? Okay. Um, Thank you, sir. Thank you very much, sir, for sharing such an informative practical session on solar inverters, its features, and various control mechanisms. Thank you very much, sir.
Thank you to give me the opportunity for this lecture. Thank
Thank
you.
you. Thank you very much. Dear all, I have shared one feedback form in the chat box. Please fill the feedback form and we'll meet tomorrow for the next session, that is session number 3 at 11 a.m. tomorrow. Thank you, everyone.